Every detail in this story comes from real scientific research and observation. There are places in space where the forces of the universe cancel each other out. Not metaphorically, mathematically. 5 specific points in every two-body gravitational system where the pull of two massive objects and the push of orbital mechanics reach an exact equilibrium where an object placed there will stay, held by the geometry of space itself. They cannot be seen. They have no surface, no mass, no light. They are not objects. They are locations, pure mathematics carved into the fabric of the solar system. Right now, at this moment, a telescope the size of a tennis court is hovering at one of these points. It has been there for over 3 years. It is operating at a temperature of -233 degrees Celsius, colder than any natural object in the solar system. And it is sending back images of galaxies that formed less than 300 million years after the Big Bang. It is parked in empty space, and it is not moving because it does not need to. There is a point between the Earth and the Sun, 1,500,000 kilometers from Earth, where the gravitational pull of the Sun and the gravitational pull of Earth combine with the centrifugal effect of orbital motion to create a region of near-perfect balance. A spacecraft placed here orbits the Sun at exactly the same speed as Earth. It stays between the Earth and the Sun indefinitely. It watches the solar wind approach Earth from 15 to 60 minutes before that wind arrives. It is a warning station, a sentinel, positioned in a place a mathematician calculated with a pen in 1772. There is a population of asteroids in the solar system that has been trapped in gravitational balance for 4.5 billion years. They have never escaped. They have never significantly changed their orbits. They circle the Sun 60 degrees ahead of Jupiter and 60 degrees behind it, locked in the same invisible structure that holds Webb above the dark side of Earth. Some of them may contain the raw organic chemistry that seeded life on this planet. They have been there since before Earth existed. A spacecraft was launched in October of 2021 to visit them. It will spend 12 years traveling between 7 of these ancient objects before its mission ends. No spacecraft has ever done this before. At one of these balance points, one that sits 60 degrees behind the Earth in its own orbit, there may be a cloud of dust trapped there since the formation of the solar system. It was first proposed in 1961. For decades, no one could confirm it. In 2018, a team of astronomers in Hungary photographed it for the first time. A structure 4 times the size of the full moon in the sky, invisible to the naked eye, hanging in gravitational equilibrium above the Earth's orbital path. We did not know it was there. It had always been there. A mathematician named Joseph-Louis Lagrange published his solution to the three-body problem in 1772. He was 36 years old. He was trying to answer a question that had resisted every attempt since Newton. What happens to the motion of 3 objects when they all pull on each other simultaneously? The full problem has no general solution. It cannot be solved exactly for all possible configurations. But Lagrange found something remarkable. For certain specific geometrical arrangements, the problem becomes tractable. The 3 bodies can move in a way that preserves their relative positions indefinitely. 5 such arrangements exist. 5 points, and they are real. The geometry was there before anyone looked for it. Tonight, the story of these 5 points begins. This is quiet science at bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research, real missions, and real measurements taken by instruments currently operating in space. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. There is a problem in physics that has never been fully solved. It is called the three-body problem. It asks a deceptively simple question. Given three objects in space, each exerting a gravitational pull on the other two, how will they move over time? Two objects, two bodies is manageable. Newton solved it in the 17th century. Two masses in space will orbit their common center of mass in predictable, calculable ellipses. The math is clean. The solution is exact. Add a third body and everything changes. The gravitational interactions become coupled in ways that resist analytical solution. Small perturbations compound over time. Trajectories that appear stable can become chaotic after thousands or millions of orbits. The general three-body problem, three arbitrary masses at arbitrary positions with arbitrary velocities, has no closed-form solution. It never has. This is not a gap in current knowledge. It is a proven mathematical limitation. The equations cannot be integrated in the general case. But in 1772, Joseph-Louis Lagrange found something. He was working within a specific, restricted version of the problem. Take two large bodies, say a star and a planet, and ask what happens to a third, much smaller body, one whose own mass is negligible compared to the other two. This third object does not meaningfully affect the orbits of the two large masses. It is simply a passenger in their gravitational field. Where can this passenger sit, such that the system remains geometrically stable? Lagrange found 5 such locations. He called them equilibrium points. Today they carry his name. The 5 Lagrange points of any two-body system are the 5 positions where a small object can maintain a fixed geometric relationship with both large masses indefinitely, assuming no other perturbations. To understand why these points exist, consider what a spacecraft in orbit actually experiences. In the reference frame that rotates with the Earth-Sun system, a frame in which both the Earth and Sun appear stationary, there are 2 kinds of forces acting on any object. First, there is the direct gravitational attraction of both the Sun and Earth, pulling the object toward each of them with a force that depends on distance and mass. Second, there is what physicists call the centrifugal force, an apparent outward push that arises because this rotating reference frame is non-inertial. In this frame, an object that is not accelerating feels a centrifugal push outward from the system's center of mass. These forces do not cancel each other everywhere. They cancel at 5 specific points. The first 3, L1, L2, and L3, lie along the line connecting the 2 massive bodies. L1 sits between the Sun and Earth on the direct line connecting them at a distance of approximately 1,500,000 kilometers from Earth. At this location, the gravitational pull of the Sun and the gravitational pull of the Earth combine with the centrifugal effect to produce a net force of 0. An object at L1 orbits the Sun with exactly the same angular velocity as Earth, meaning it keeps pace with the planet despite being closer to the Sun and therefore, by Kepler's laws, having a shorter natural orbital period. The reduced solar gravity at L1, partially canceled by Earth's pull from behind, compensates for this discrepancy. L2 sits on the opposite side of Earth from the Sun, also approximately 1,500,000 kilometers away. Here, the Sun's gravity and Earth's gravity both pull in the same direction, toward the Sun, while the centrifugal force pushes outward. At L2 specifically, the sum of these forces equals 0. An object here orbits the Sun at the same rate as Earth despite being farther from the Sun, because the combined inward pull of both the Sun and Earth makes up for the orbital energy deficit. L3 lies on the far side of the Sun from Earth, at approximately the same orbital radius as Earth, but on the directly opposite side of the solar system. It is the weakest of the 5 points and the least useful for practical purposes. Its distance from Earth, nearly twice Earth's orbital radius, and its permanent solar occlusion make it inaccessible for most mission profiles. L4 and L5 are fundamentally different. They do not lie on the Sun-Earth line. They sit along Earth's orbital path, 60 degrees ahead of and 60 degrees behind the Earth respectively. L4 leads Earth in its orbit, L5 trails behind it. These 2 points form equilateral triangles with the Sun and Earth, each side of the triangle equal to 1 astronomical unit, the Sun-Earth distance. The reason L4 and L5 are stable requires a more careful analysis than the collinear points. At L1, L2, and L3, the equilibrium is what mathematicians call an unstable saddle point. Imagine a marble balanced on a mountain pass, a ridge with a valley on either side. The marble sits at the high point between 2 slopes. It is technically in equilibrium, but any displacement along one axis will cause it to roll away. A small push in the wrong direction and the equilibrium is broken. Spacecraft at L1 and L2 must continuously perform small corrective maneuvers, called station keeping, to maintain their positions. Without these corrections, they drift away within weeks or months. L4 and L5 are different because the equilibrium there is stable under certain conditions. The stability of L4 and L5 was proven analytically in Lagrange's original work, but it requires a specific mass ratio between the 2 primary bodies. The mass of the larger body, in this case the Sun, must be at least 24.96 times the mass of the smaller body, the Earth. The Sun is approximately 333,000 times the mass of Earth. The condition is satisfied easily. When this condition is met, any object displaced slightly from L4 or L5 experiences a restoring force, not directly back toward the equilibrium point, but in a way that causes the object to orbit around the point. This orbital motion is driven by the Coriolis effect, the same force that causes Earth's large-scale atmospheric circulation to rotate. In the co-rotating reference frame, a displaced object at L4 or L5 begins to circulate, and the interplay between gravity and Coriolis deflection prevents it from escaping. The object librates, oscillating around the equilibrium point in a slow, stable pattern. This is why the Trojan asteroids of Jupiter have remained at L4 and L5 for billions of years. The stability is not approximate, it is real, and it is durable across geological timescales. The physical scale of these points in the Sun-Earth system is worth pausing on. L1 and L2 are each approximately 1,500,000 kilometers from Earth. To put this in perspective, The Moon orbits at an average distance of 384,000 kilometers. Ella 1 and L2 are roughly 4 times farther from Earth than the Moon. In terms of travel time, at the speed of light, a signal from Earth reaches L1 or L2 in approximately 5 seconds. In terms of spacecraft travel, a direct trajectory from Earth to L2 takes roughly 3 to 4 months. Ella 4 and L5 in the Sun-Earth system are each approximately 1 astronomical unit, 150 million kilometers from Earth, sharing Earth's orbital path but displaced by 60 degrees. A spacecraft sent to Sun-Earth L4 or L5 would need to travel along Earth's orbit, essentially racing ahead of or behind the planet by 60 degrees of arc. This is not currently done for operational missions, partly because of the travel distance, and partly because the region lacks the unique thermal and observational advantages of L2. L3 sits at roughly 2 astronomical units from Earth at closest approach on the far side of the Sun and has never hosted an operational spacecraft. The points are not small. They do not refer to a single precise location because of the finite masses involved, because of perturbations from other planets, and because of practical engineering constraints. What is operationally useful is not a point but a region. Spacecraft do not park at an exact point. They orbit around it in trajectories called halo orbits or Lissajous orbits, structured paths that circle the equilibrium region while using minimal fuel to maintain their approximate position. These orbits exist because of the saddle point geometry of L1 and L2. In the vicinity of L1 or L2, the effective gravitational potential has a shape that permits certain orbital families. Robert Farquhar, an American aerospace engineer at NASA's Goddard Space Flight Center, first calculated the properties of halo orbits in the 1960s. His doctoral dissertation was on the subject. He spent years trying to convince NASA mission planners that these orbits were practically useful, that a spacecraft could be sent to a Lagrange point and held there indefinitely with a manageable fuel budget. He was eventually proven right, but that confirmation came only when the hardware was actually built and launched. The mathematics of Lagrange points belongs to the late 18th century. The first operational use of them belongs to the late 20th. That gap, 200 years, reflects the gap between knowing a location exists and being able to reach it, operate there, and do useful science from it. What Lagrange computed was, in a sense, a map of invisible infrastructure. 5 locations in every 2-body gravitational system in the universe, around every star with a planet, around every planet with a moon, where the geometry of motion creates a natural anchor point. They exist around the Sun and Jupiter, around the Sun and Saturn, around the Earth and Moon, around Neptune and its largest Trojan companions, around binary stars, around any system large enough to generate a gravitational field strong enough to hold something at equilibrium. The solar system is not empty space punctuated by objects. It is a structured field of gravitational geometry, and Lagrange points are among its most precise features. The architecture was always there. We simply learned to read it. Lagrange himself did not anticipate operational spacecraft. He was solving a mathematical problem. The application to actual space mission design would take nearly 2 centuries. The invention of the rocket, the development of orbital mechanics as an engineering discipline, and eventually the construction of instruments sensitive enough to make parking at a Lagrange point worthwhile. The first instrument that made it worthwhile was a solar observatory. The sun is a variable star. Its output fluctuates. Its surface churns with magnetic activity that periodically erupts in events called coronal mass ejections. Billions of tons of magnetized plasma launched at speeds between 200 and 3,000 kilometers per second directly into the solar system. When this plasma reaches Earth, it interacts with the planet's magnetic field in ways that can disrupt satellite operations, power grids, and radio communications. To predict these events, to give even 15 minutes of warning, requires continuous observation of the sun from a location that never loses sight of it. Earth-based observatories are interrupted by night. Low Earth orbit satellites pass behind Earth. What was needed was a position from which the sun was always visible, always unobstructed, and from which a signal could reach Earth quickly enough to be useful. L1 provided that position. A spacecraft at L1 sits between Earth and Sun, with the Sun permanently in its field of view and with Earth visible behind it. Signals travel from L1 to Earth in approximately 5 seconds, and the solar wind, the continuous stream of charged particles flowing outward from the Sun, passes through L1 before it reaches Earth. A detector at L1 can measure the properties of incoming solar wind before it strikes Earth's magnetosphere. 15 to 60 minutes of warning. That is what the geometry buys. This was the scientific justification that finally sent hardware to a Lagrange point. The first spacecraft to make the journey launched in 1978. Its name was ISEA-3, the International Sun-Earth Explorer 3. It was a joint mission between NASA and the European Space Agency. Its primary scientific goal was to study the solar wind and its interaction with Earth's magnetic environment, and it was the first operational demonstration that a spacecraft could be placed in a halo orbit around L1, held there by periodic station-keeping maneuvers, and used as a continuous scientific platform. IC-3 arrived at its L1 halo orbit in November of 1978. It operated there for 3.5 years. The mission confirmed what Farquhar and others had calculated, that the fuel required to maintain station at L1 was modest, that the orbit was achievable with the propulsion systems of the era, and that continuous solar observation from that position was genuinely scientifically valuable. What followed ICE-3 was a slow expansion of operations at L1, each mission more capable than the last, each one building on the infrastructure of knowledge that had been accumulated since Lagrange published his solution. The equilibrium he found was not theoretical curiosity. It was the first entry in an operational catalog that would eventually include telescopes seeing back to the edge of time, warning systems protecting power grids on Earth, and traps holding asteroids in the same orbital positions they occupied before the first animals appeared on this planet. The 5 points are not equal. They do not all serve the same purpose. They do not all offer the same stability, the same accessibility, the same scientific value. Each has a distinct character defined by its geometry, its distance, its relationship to the two bodies that generate it. L1 faces the Sun, L2 faces the universe, L4 and L5 face the past. And the story of what humanity has placed at each of them and what it has found there is a story about the architecture of the solar system, the limits of human engineering, and the slow translation of a mathematician's abstract solution into the most precise instruments our civilization has ever built. That story continues now, in the dark, in the silence between the stars. The solar system did not arrive at its current configuration through randomness alone. It was shaped by forces, gravity, collision, radiation, pressure, resonance, and over 4.5 billion years, those forces sorted matter into structures that persist because they are stable. The orbits of the planets are not arbitrary. The distribution of asteroids is not chaotic. The locations of Lagrange points are not accidents. They are the natural geometry of a gravitational system, as inevitable as the angles of a crystal. Every planet that orbits the Sun generates its own set of 5 Lagrange points in relation to the Sun. Jupiter's L4 and L5 hold more than 13,000 known asteroids. Mars has its own Trojans. Neptune has its own. Earth has its own. The Moon, in orbit around Earth, generates a second set of Lagrange points in the Earth-Moon system, points that are different in scale, different in stability characteristics, and different in their practical applications from the Sun-Earth points. The solar system is threaded with these locations. They are everywhere. Most of them hold nothing operational. Most of them have never been visited, but they are there, waiting in the mathematics of gravitation, part of the hidden architecture of the solar system that was computed before the telescope was invented and is only now beginning to be understood as infrastructure. The 5 points Lagrange found are not a curiosity, they are a feature of the universe. Any 2 massive objects in orbit around each other generate them. The Earth and Moon have them. Jupiter and its major moons have them. Binary stars have them. Exoplanets and their host stars have them. Wherever gravity organizes 2 masses into an orbital relationship, 5 equilibrium points exist in the space around them, shaping the motion of anything small enough to be subject to both gravitational fields simultaneously. This is not a small thing. It means that the solar system contains not just the planets and moons and asteroids and comets that can be directly observed. It contains a second layer, an invisible scaffolding of gravitational equilibrium points, each one a potential anchor, a potential trap, a potential observatory platform, a potential way station for future missions deeper into the solar system. Lagrange mapped the scaffolding. It took humanity 2 centuries to learn to use it. And the work is only just beginning. The night is quiet now. The mathematics of 3 bodies and mutual attraction is playing out in the solar system above, as it has been since the planets formed from the disk of gas and dust that surrounded the young sun. Asteroids librate slowly around their equilibrium points. Spacecraft perform their quiet station-keeping burns, a few meters per second of velocity change every few weeks, burning a few grams of propellant, maintaining a position that was first calculated with paper and quill in the 18th century. The Sun is approximately 1,500,000 kilometers from the instruments at L1, seen from Earth's perspective. The instruments at L2 face the other direction, into the cold dark, toward the cosmic microwave background, toward the oldest light in the universe. Between these 2 directions, between the heat of the sun and the cold of the deep sky, is the Earth, turning slowly, orbiting at 30 kilometers per second. Generating, with its gravity, 5 points of equilibrium in the space around it. 5 locations where the geometry of motion produces silence. Not the silence of emptiness. The silence of balance. L1 and L2 are not stable. This is the first thing to understand about them. They are equilibrium points, but they are the wrong kind of equilibrium. The balance they offer is like the balance of a ball resting on top of a hill. Technically valid, mathematically real, but inherently fragile. Any displacement, no matter how small, will cause the ball to roll away. The equilibrium is not self-correcting, it is self-destroying. In the language of dynamical systems, L1 and L2 are saddle points. A saddle point has the property of being simultaneously a local maximum in one direction and a local minimum in another. Think of the shape of a mountain pass, the lowest point on a ridge between two peaks. A rider traveling through the pass is at the highest point along the left-right direction, but at the lowest point along the forward-backward direction. A ball placed at the center of a saddle will roll sideways and fall off the saddle immediately. At L1 and L2, the gravitational potential surface has exactly this saddle geometry. In the direction along the Sun-Earth line, L1 and L2 are potential minima. An object displaced along this axis is pushed back toward the equilibrium point, but in the perpendicular directions, sideways and up-down relative to the orbital plane, L1 and L2 are potential maxima. An object displaced in those directions rolls away from the equilibrium point and continues moving away indefinitely. A spacecraft placed with perfect precision at the exact L1 point, with zero velocity relative to the rotating reference frame, would stay there. But perfect precision is not achievable. Every thruster firing has a small error. Every gravitational perturbation from Jupiter or Venus or Mars nudges the spacecraft slightly. Every time the spacecraft transmits a radio signal or experiences solar radiation pressure, its trajectory is affected by a tiny measurable amount. In practice, a spacecraft placed at L1 with any realistic level of navigational accuracy will begin drifting within days. This is why Robert Farquhar's work in the 1960s was essential. Farquhar realized that the saddle geometry of L1 and L2, while preventing a spacecraft from simply sitting at the exact equilibrium point, did permit a different kind of trajectory in the vicinity of these points. The same instability that would cause a spacecraft to drift away also created the conditions for periodic orbits, closed or nearly closed paths that circled around the equilibrium region without escaping. These are called halo orbits. The name comes from their visual appearance when projected against the solar disk, as seen from Earth. A spacecraft on a halo orbit at L1 traces an elliptical path that, when seen from Earth, appears as a ring, a halo, centered on the Sun. Farquhar coined the term in his doctoral work at Stanford University in 1968. The physics of a halo orbit is subtle. It exploits the fact that near a saddle point, the restoring force along one axis and the destabilizing force along the perpendicular axis can, under the right conditions, be balanced against each other through the addition of an out-of-plane component to the spacecraft's motion. A spacecraft given a carefully calculated initial velocity in the direction perpendicular to the orbital plane, away from the flat disk of the solar system, will follow a three-dimensional path that neither escapes from the L1 region nor collapses toward the equilibrium point. It orbits the L1 region in a slow, looping path. The orbit is not naturally stable. It requires periodic correction. These corrections are called station-keeping maneuvers. A A typical station-keeping maneuver for a spacecraft in a halo orbit around L1 or L2 involves a very small change in velocity on the order of 1 to 10 meters per second, applied approximately every 3 to 4 weeks. The total station-keeping budget for a mission lifetime of several years amounts to a few tens of meters per second of delta V. In terms of propellant mass, for a spacecraft of typical size, this translates to a few kilograms of fuel per year. This is a remarkably small cost. It is what makes L1 and L2 operationally viable. The alternative to station keeping at L1 or L2 would be a continuous powered orbit, essentially flying a spacecraft around the Sun at the right distance while firing its engines constantly to maintain the correct speed. This would require vastly more propellant and would be impractical for any long-duration mission. The halo orbit solution trades an exact impossible equilibrium for an approximate, manageable one. The spacecraft is never exactly at L1 or L2. It is always slightly off, looping around the equilibrium region in a slow, fuel-efficient path that keeps it statistically close to the point without requiring continuous propulsion. It is not stillness. It is the controlled appearance of stillness. A related family of trajectories, called Lagrange orbits, exists in the same region. Lagrange orbits are named after the French physicist Jules-Antoine Lagrange, who studied the interference patterns of two oscillating systems in the 19th century. In the context of Lagrange point dynamics, a Lagrange orbit arises when the in-plane and out-of-plane oscillations around the equilibrium point have different frequencies, resulting in a trajectory that traces a complex quasi-periodic path rather than a closed loop. Halo orbits are a specific subset of the Lagrange family in which the two oscillation frequencies are forced into resonance, a precise mathematical condition that produces a closed path. This resonance condition requires a specific amplitude of the out-of-plane component, which is why not all initial conditions near L1 or L2 produce halo orbits. Mission designers must calculate the required initial conditions precisely and then target them during the launch and cruise phase. IC-3, the first spacecraft to operate at a Lagrange point, used a halo orbit around L1. Its orbit had a radius of approximately 15,000 kilometers and a period of approximately 6 months. The spacecraft circled the L1 region once every 6 months, completing its solar wind monitoring mission while performing small periodic corrections to maintain the orbit. The ICE-3 mission validated everything Farquhar had calculated. The halo orbit worked. The station-keeping requirements were within budget. The science was exactly what the mission planners had anticipated. Solar wind measurements from L1 provided the first continuous, unobstructed time series of the properties of the solar wind approaching Earth, measurements that could not be obtained from any other orbital location. The legacy of ICE-3 is the operational paradigm that every subsequent L1 and L2 mission has followed. It is the proof of concept that turned a mathematical abstraction into a standard mission profile. The next major mission to operate at L1 arrived 17 years later. SOHO, the Solar and Heliospheric Observator, launched on December 2, 1995. It was a joint mission between NASA and the European Space Agency, designed to study the Sun in unprecedented detail across multiple wavelengths simultaneously. Its instruments could observe the Sun's corona, track the propagation of solar wind, detect solar oscillations, and monitor the properties of the heliosphere. SOHO arrived at its L1 halo orbit in February of 1996. It is still there. As of 2026, SOHO has been operating continuously at L1 for more than 30 years. It is one of the longest-running space science missions in history and one of the most productive. It has produced over 4,000 scientific publications. It has provided near-continuous solar observation for 3 complete 11-year solar cycles. It has monitored the sun through solar minimum, solar maximum, and back again, building a data archive that spans more than a quarter century. SOHO's instruments include 12 separate scientific packages covering ultraviolet imaging, coronagraphs, spectrometers, particle detectors, and magnetometers. Its coronagraphs, instruments that block the direct solar disk to allow imaging of the faint corona around it, have incidentally become the most prolific comet discovery instruments in history. More than 4,000 comets have been discovered in SOHO's coronagraph data, most of them by citizen scientists analyzing the publicly available images. Many of these comets are sun grazers, members of the Cretes group, fragments of a large comet that broke apart sometime in the past, and they were found because SOHO's position at L1 allowed continuous coronagraph imaging without the day-night interruptions of Earth-based observatories. A solar observatory, parked at a balance point, became the greatest comet hunter in history. SOHO was followed to L1 by a growing cluster of spacecraft, each adding a different sensor to the monitoring network. AC, the Advanced Composition Explorer, launched in 1997. It carried 9 separate instruments for measuring the composition and energy of charged particles from the solar wind, the galaxy, and beyond. Its position at L1 placed it in the path of the solar wind before that wind reached Earth, allowing continuous measurement of the elemental and isotopic composition of solar wind particles, data that feeds models of solar activity, solar energetic particle events, and the physics of stellar wind in general. AC's position at L1 means it measures the solar wind approximately 15 to 60 minutes before that same wind reaches Earth. The exact timing depends on solar wind speed, fast streams at 700 to 800 kilometers per second, slow streams at around 400. The journey from L1 to Earth takes between 30 minutes and an hour. This lead time is operationally significant. When ACE detects an incoming coronal mass ejection, a large eruption of magnetized plasma from the sun, the data can be transmitted to ground controllers who issue alerts to satellite operators, power grid managers, and other infrastructure operators. The alert is not always enough time to take protective action, but it is enough time to put systems into a protective mode that reduces their vulnerability to geomagnetic storm effects. The 2003 Halloween solar storms, a series of exceptionally powerful coronal mass ejections in late October and early November of that year, were among the most intense recorded in the modern space age. They caused widespread satellite anomalies, disrupted high-frequency radio communications, and produced aurora visible as far south as the Mediterranean. The L1 early warning network detected the incoming plasma and issued alerts. The storms were still damaging, but without the L1 measurement network, the damage would have been greater. WIND, another spacecraft in the L1 cluster, has been measuring plasma, energetic particles, and magnetic fields since 1994. Originally placed in a complex Earth orbit before being moved to L1, WIND provides complementary solar wind measurements to ACE and SOHO, with particular sensitivity to low-frequency plasma waves and particle acceleration mechanisms in the solar wind. DSEOV-AIR, the Deep Space Climate Observatory, arrived at L1 in 2015. Its primary operational mission is to provide real-time solar wind data to NOAA's Space Weather Prediction Center. DSEOV-AIR carries magnetometers and plasma sensors that measure the properties of the solar wind, speed, density, temperature, and magnetic field orientation, approximately 15 to 60 minutes before those properties reach Earth. This data feeds operational space weather forecasting services that are used by satellite operators, power utilities, and aviation controllers worldwide. DSEOVR also carries an Earth imaging instrument called EPIC, Earth Polychromatic Imaging Camera, which photographs the entire sunlit face of Earth once every 1 to 2 hours. Because DSEOVR sits between Earth and Sun, EPIC always sees the sunlit hemisphere of Earth, a perspective that no other operational spacecraft provides continuously. The images are used to monitor vegetation, ozone, cloud cover, and aerosol properties across the globe. The same orbit that watches the Sun also watches the Earth. The L1 cluster, SOHO, ACE, WIND, DiscoVR, and others forms an informal but operationally critical network. These spacecraft do not coordinate directly with each other in any formal sense. They simply share a location, and that shared location gives them a shared set of scientific and operational advantages. Together, they provide continuous redundant monitoring of the solar wind from the only position in the solar system from which the wind can be measured before it reaches Earth. This network exists because of a mathematical solution published in 1772. It exists because Robert Farquhar spent a decade convincing mission planners that halo orbits were real and manageable. It exists because ICE-3 demonstrated the concept successfully. And it exists because the saddle point instability of L1, the very property that makes it impossible to simply park a spacecraft there, also creates the orbital families that allow spacecraft to hover in the vicinity efficiently. The instability is not a flaw. It is a feature that was eventually understood and exploited. This is often how the most useful discoveries in applied physics work. A property that appears to be a limitation turns out, on closer examination, to be a resource. The saddle geometry of L1 and L2 looked like a problem. Farquhar saw it as a solution. And now, while the Earth turns below, while the aurora occasionally flares at the poles in response to solar wind pressure, there is a collection of aging spacecraft held in slow, looping paths around an invisible mathematical point 1.5 million kilometers sunward of Earth, measuring, transmitting, cataloging, doing exactly what the geometry of two gravitational fields and a rotating reference frame permits them to do. The instruments are cold, the solar panels are slowly degrading, the propellant reserves are finite. But the orbits continue. And on the other side of the Earth, facing not the sun but the dark, a different set of spacecraft sit at L2, looking in the opposite direction entirely. L2 offers something that L1 cannot. L1 faces the sun. It is oriented toward heat, toward radiation, toward the relentless electromagnetic output of a star. The instruments at L1 must be designed to withstand solar radiation, to tolerate high-energy particle bombardment, to operate in the brightest electromagnetic environment in the inner solar system. L2 faces away from the sun. It sits on the night side of Earth, in the shadow of both the Earth and the sun. The sky in every direction away from the Sun-Earth line is cold, dark, and filled with the most ancient light in the universe. For telescopes that need cold, dark sky, that need to detect infrared radiation from objects billions of light years away, that need to measure temperature variations of 1 part in 100,000 in the cosmic microwave background, L2 is the only viable location in the inner solar system. L2 is where the universe opens up. And that story belongs to the next part of the night. The transition between L1 and L2 is, in a physical sense, a simple one. Both points sit at approximately the same distance from Earth, 1,500,000 kilometers. Both require halo orbits to remain operationally accessible. Both are reached by similar trajectory profiles from Earth. A spacecraft designed for L2 and a spacecraft designed for L1 would follow nearly identical launch and transit phases before diverging in the final approach, one heading sunward and the other heading into shadow. But the scientific meaning of these two directions could not be more different. At L1, every instrument faces a star, a source of light, heat, and radiation that must be managed, shielded, and accounted for in every measurement. The science of L1 is the science of proximity, measuring what the sun does, what it releases, how it fluctuates, how its output propagates through the space between. At L2, every instrument faces the dark. The sun is permanently behind the spacecraft, blocked by the combined geometry of the sun, Earth, and a spacecraft sunshield. The temperature in the direction away from the sun drops to a few Kelvin above absolute zero. The photon background is as low as anywhere accessible within the inner solar system. For infrared astronomy, this is not merely convenient, it is essential. Infrared light, electromagnetic radiation with wavelengths longer than visible light, ranging from roughly 1 micron to several hundred microns, is produced by everything that has temperature. Every object warmer than absolute zero radiates infrared light. The Earth radiates infrared. The Moon radiates infrared. A spacecraft and its instruments radiate infrared. And when attempting to detect the faint infrared signal from a galaxy 12 billion light-years away, your own instruments and thermal environment represent a source of noise that must be reduced as far as physics allows. Reducing instrument temperature is the primary way to reduce this noise. Cold detectors are less sensitive to their own thermal background and more sensitive to external signals. The colder the instrument, the fainter the signal it can detect. At Earth's surface, even on the highest, driest mountain, the atmosphere absorbs most infrared wavelengths. In low Earth orbit, the Earth itself fills half the sky and radiates thermal energy continuously. Even in a geosynchronous orbit, the Earth and Moon are bright infrared sources that contaminate measurements. At L2, 1,500,000 kilometers from Earth, with the sunshield blocking the Sun, Earth, and Moon simultaneously, the thermal environment is as clean as anywhere a spacecraft can reach within a few months of travel. The sky temperature in the cold direction is approximately 2.7 Kelvin, the temperature of the cosmic microwave background itself. This is the physical justification for locating observatories at L2. Not merely convenience, not merely stability. The location is required by the physics of the measurements being attempted. The first major observatory deployed to L2 was WMAP, the Wilkinson Microwave Anisotropy Probe, launched in June of 2001. WMAP's scientific goal was to map the cosmic microwave background with unprecedented precision. The cosmic microwave background is the thermal afterglow of the early universe, the remnant radiation from the epoch of recombination, approximately 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and the hot plasma that had filled all of space became transparent. Before recombination, the universe was opaque. Photons could not travel freely through the ionized plasma. After recombination, the photons already present in the universe streamed freely in all directions, and they have been traveling ever since. Today, those photons have been stretched by the expansion of the universe to microwave wavelengths. They arrive at Earth from every direction with almost perfect uniformity. The temperature of the cosmic microwave background is approximately 2.725 Kelvin, measured to the 5th decimal place. The variations in this temperature from point to point across the sky are on the order of 1 part in 100,000. 1 part in 100,000. To detect a signal this faint against a microwave background that is itself extremely cold requires instruments operating at temperatures close to absolute zero, deployed in an environment as thermally stable and contamination-free as possible. L2 was the only practical location for this instrument within the solar system. WMAP operated for 9 years. It produced the most detailed full-sky map of the cosmic microwave background available at the time of its decommission in 2010. From that map, cosmologists extracted measurements of the age of the universe, 13.77 billion years, with an uncertainty of less than 1%. They extracted the composition of the universe, approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. They extracted the geometry of the universe, flat to within measurement precision, meaning the total energy density is equal to the critical density that separates a universe that expands forever from one that eventually collapses. All of this from a temperature map of the sky. All of this from temperature variations of 1 part in 100,000. All of this from an observatory parked at L2, a mathematical point discovered in 1772 held the instrument that told us how old the universe is. WMAP was followed by Planck, a European Space Agency mission launched in May of 2009 alongside the Herschel Space Observatory, 2 spacecraft on the same rocket deployed to L2 simultaneously. Planck improved on WMAP's angular resolution and sensitivity by a factor of several times. Its detectors, bolometers, cooled to a temperature of 0.1 Kelvin, 1/10 of a degree above absolute zero, were the coldest objects in space at the time of their operation. Planck produced the definitive measurement of the cosmic microwave background temperature fluctuations, confirming and refining the WMAP results with higher precision. The Planck data released in 2013 and 2015 produced measurements of cosmological parameters, the 6 numbers that define the standard model of cosmology, with uncertainties at the level of a few tenths of a percent. The age of the universe refined to 13.82 billion years. The Hubble constant, the rate of current cosmic expansion, measured at 67.4 kilometers per second per megaparsec. These measurements represent the state of knowledge about the structure and history of the universe, obtained from an observatory that existed in part because of its location at a gravitational equilibrium point computed by an 18th century mathematician. Herschel, launched on the same rocket as Planck, operated in a different wavelength range, far infrared, from roughly 55 to 670 micrometers, and addressed different scientific questions. It studied the formation of stars and galaxies, the properties of molecular clouds, the chemistry of planetary atmospheres, and the debris disks around other stars. Like Planck, its primary science drivers required a cold, dark sky with stable thermal conditions provided only by L2. Herschel operated for over 3 years before its liquid helium coolant was exhausted in April of 2013. When the coolant ran out, the instrument temperatures rose and the science capability ended. The spacecraft was placed in a parking orbit around the Sun and its operational mission was concluded. But the data from Herschel continued to produce scientific results for years after the mission ended. Science archives accumulated from instruments at L2 have a long scientific half-life. They continue to be analyzed, reanalyzed, and cross-referenced with data from new instruments for decades. This is part of the value of L2 as a location. The observatory platforms deployed there are capital infrastructure in a way that ground-based observatories are. The investment in the launch, the trajectory design, the thermal engineering, all of it compounds over time as the data archives grow and the analysis community has time to extract every possible measurement from the recorded photons. Gaia, launched in December of 2013 and still operational in 2026, approaches L2 science from a completely different direction. Not cosmology, but astrometry. Astrometry is the precise measurement of the positions and motions of stars. It is one of the oldest branches of astronomy and one of the most exacting. Measuring the position of a star to high precision requires a stable platform, one that is not perturbed by atmospheric seeing, not subject to thermal expansion cycles, not vibrated by mechanical systems, and not limited by the day-night interruptions that affect ground-based observatories. Gaia was designed to measure the positions of approximately 1 billion stars across the Milky Way with an angular precision of micro-arcseconds. 1 micro-arcsecond is the angle subtended by a human hair at a distance of approximately 10,000 kilometers. This precision requires a platform so stable that even the photon pressure of starlight striking the spacecraft is accounted for in the instrument calibration. Gaia operates in a Lagrange orbit around L2, slowly scanning the entire sky in a pattern that allows each star to be observed dozens of times over the mission lifetime. The redundancy in observations allows systematic errors to be identified and corrected, and the precision of individual position measurements to be validated. The Gaia data releases, the first in 2016, the most recent as of 2022, have transformed our understanding of the structure and history of the Milky Way. The positions and velocities of more than 1 billion stars can be used to reconstruct the past orbits of those stars, identifying the remnants of ancient merger events in which smaller galaxies were absorbed by the Milky Way over billions of years. The three-dimensional map of stellar positions and motions that Gaia is building will take decades to fully analyze. All of it made possible by an orbit around an invisible point in space. The night continues, the orbit continues, the instruments face the dark. And somewhere in the data stream, in the sequence of photons that have been traveling for 13 billion years and are now arriving at a gold mirror, cooled to minus 233 degrees Celsius, is a signal that was released before the Milky Way galaxy finished forming. That mirror and the telescope around it and the orbit it traces around L2 belong to the next chapter of this story. On December 25th, 2021, a rocket lifted off from the Guiana Space Center in Kourou, French Guiana, and carried into orbit the most complex scientific instrument humanity had ever built. The launch was an Ariane 5 rocket. The payload was the James Webb Space Telescope. The destination was L2, the second Lagrange point of the Sun-Earth system, 1,500,000 kilometers from Earth in the direction away from the Sun. The journey to L2 took approximately 29 days. The deployment of the telescope systems took another 5 months. What happened during those 5 months was, by any engineering measure, the most elaborate and anxiety-inducing sequence of mechanical operations ever attempted in space. The James Webb Space Telescope could not be launched in its operational configuration. It was too large. The primary mirror, a hexagonal array of 18 gold-coated beryllium segments, spans 6.5 meters in diameter. The sunshield, a 5-layer membrane of Kapton film, each layer thinner than a human hair, designed to reduce the temperature difference between the sun-facing and space-facing sides of the telescope from approximately 185 degrees Celsius to minus 233 degrees Celsius, spans 21 meters by 14 meters when fully deployed. Neither the mirror nor the sunshield fit inside any existing rocket fairing in their operational configurations. Both had to be folded. The telescope was designed to unfold itself after launch, in the cold and vacuum of space, through a sequence of 344 individual mechanical deployments: hinges, latches, motors, release mechanisms, tension cables, each one necessary for the instrument to reach its operational state. 344 steps. None of them could be tested in exactly the conditions they would face in space. None of them could be reversed if they failed. Each one had to work the first time, in the cold, in the vacuum, 250,000 kilometers from Earth, by the time the critical sunshield deployment began. Any single one of those steps, if it had failed, would have ended the mission before a single photon was collected. All 344 succeeded. The sunshield deployed over a period of approximately 8 days following launch. The primary mirror unfolded over the following week. By mid-January 2022, the telescope was in its operational configuration, a cold, gold hexagonal mirror facing the dark sky, shielded on the sun-facing side by the 5-layer membrane that would maintain the instrument temperatures required for infrared observation. By July 2022, after months of mirror alignment and instrument commissioning, the first science images were released. The reason L2 was chosen for Webb is the same reason it was chosen for WMAP, Planck, and Herschel, but Webb's requirements pushed the rationale to an extreme that no previous mission had approached. Webb observes primarily in the near-infrared and mid-infrared, wavelengths ranging from approximately 0.6 to 28 microns. At these wavelengths, the primary sources of noise are thermal emission from the telescope and its surroundings. Every warm object emits infrared light, proportional to its temperature. For Webb to detect the infrared signal from a galaxy that formed 300 million years after the Big Bang, a galaxy at a redshift of approximately 10, where the original ultraviolet and visible light has been stretched to near-infrared by the expansion of the universe, the telescope's own thermal emission must be suppressed to an extraordinary degree. Webb's primary mirror operates at approximately 50 Kelvin, minus 223 degrees Celsius. Its mid-infrared instrument, MIR-EIE, requires cooling to 6.7 Kelvin, just 6.7 degrees above absolute zero, achieved through a combination of passive radiative cooling and an active cryocooler. These temperatures are achievable only because of where the telescope is located. At L2, with the sun shield blocking all direct solar, terrestrial, and lunar radiation, the passive radiative cooling of the telescope's cold side proceeds uninterrupted. The telescope radiates its own thermal energy into the cold sky and reaches thermal equilibrium at temperatures that would be impossible to achieve in low Earth orbit, where Earth's own thermal emission would continuously warm the instrument. The location is not incidental to the science. The location is the science. Webb's primary mirror consists of 18 hexagonal segments, each 1.32 meters across, and coated with a thin layer of gold. Gold was chosen because it reflects infrared light more efficiently than aluminum or silver at the wavelengths Webb observes. Each segment is mounted on actuators that allow its position and curvature to be adjusted with nanometer precision. 1 nanometer is 1/1000th of a meter. The 18 segments must collectively behave as a single mirror accurate to within approximately 150 nanometers across the entire 6.5 meter aperture. This alignment was achieved in space at operational temperature over a period of several weeks following deployment. Ground controllers sent commands to the actuators of each segment, adjusting their positions iteratively until the combined wavefront error, the deviation of the mirror surface from the ideal paraboloid, was reduced below the target. The result is a mirror that can collect light from objects too faint and too distant to be detected by any previous telescope. The alignment was done from 1.5 million kilometers away, one actuator command at a time. Webb's 4 scientific instruments, NIRCam, NIRSpec, NIRIS, and MIRI, cover complementary wavelength ranges and observing modes. NIRCam is the primary near-infrared imager, responsible for the deep field images that have become the most widely recognized products of the mission. NIRSpec is a multi-object spectrograph capable of measuring the spectra of up to 100 objects simultaneously, determining their redshifts, compositions, and physical conditions in a single observation. NIRIS provides additional imaging and spectroscopic capabilities. MIRI extends coverage to mid-infrared wavelengths, enabling observation of cooler objects and longer wavelength phenomena. The first deep field image released in July 2022, SMACS 0723, showed a gravitational lensing cluster at a redshift of approximately 0.39, with background galaxies at redshifts reaching beyond 8, corresponding to light that left those galaxies more than 13 billion years ago. The exposure time for the NIRCam observation was approximately 12.5 hours. In that 12.5 hours, Webb collected photons that had been traveling through the universe for more than 90% of its current age. Subsequent observations produced even more distant detections. The galaxy candidate C-AIRS 93316 was initially estimated to have a redshift above 16, placing it within 300 million years of the Big Bang, before confirmed spectroscopic follow-up refined the estimate. The confirmed galaxy JAYS GSZ 140, reported in 2024, holds the current spectroscopic distance record, with a confirmed redshift of approximately 14.32, corresponding to a time when the universe was approximately 290 million years old. The universe that Webb is observing was forming its first large-scale structures during the epoch of reionization, the period when the first stars and galaxies ionized the neutral hydrogen that had filled space since recombination. The details of this epoch, how quickly it proceeded, what drove it, how the first massive structures formed from the primordial density fluctuations, are among the primary scientific targets of the Webb mission. Webb's observations of this epoch are, in a direct physical sense, observations of the first light in the universe that could travel freely through space. L2's value for this science cannot be overstated. The stable thermal environment allows Webb to maintain its mirror temperature without active heating or cooling adjustments that would introduce vibration and pointing instability. The distance from Earth eliminates the stray light contamination that would affect observations in low Earth orbit. The unobstructed view of the full sky, rotating through the year as Earth orbits the Sun, allows Webb to observe any target in the sky at some point during the year with continuous access to the prime survey fields. Webb's designed mission lifetime was 10 years, based on the propellant budget for halo orbit station keeping and trajectory correction maneuvers. The Ariane 5 launch performance exceeded predictions, placing the telescope on a trajectory that required less trajectory correction propellant than the worst-case budget. Current estimates suggest the propellant reserve is sufficient for 20 years or more of operations. The telescope was built to last 10 years. The launch was accurate enough to give it 20. Gaia continues operating in its Lagrange orbit around L2 simultaneously with Webb. The two observatories share the L2 region, separated by hundreds of thousands of kilometers in their respective orbits, never in the same position, but both exploiting the same gravitational geometry for entirely different scientific purposes. Gaia is building a three-dimensional map of the Milky Way. Webb is building a history of the universe. Both instruments, operating simultaneously at the same Lagrange point, represent a density of scientific capability that would have seemed implausible 50 years ago. In the 1960s, when Farquhar was computing halo orbit trajectories in his doctoral dissertation, the idea that the gravitational equilibrium point he was analyzing would one day host a mirror 6.5 meters across, operating at 6 Kelvin, a mirror pointed at galaxies from 300 million years after the Big Bang, was beyond the horizon of what could be concretely planned. The mathematics was available, the location was available, the science question was available. The engineering required to connect all three was not yet available. It became available, slowly, over decades of accumulated knowledge in cryogenic engineering, mirror fabrication, spacecraft autonomy, and precision orbital mechanics, and then the connection was made. L2 is not a place in the sense that a planet is a place. It has no surface, no mass, no permanent feature. It is a mathematical property of the gravitational field, a location defined entirely by the positions and masses of the Sun and Earth and the rotational dynamics of the system. If the Earth were to suddenly increase in mass, all 5 Lagrange points would shift their positions. If the Earth's orbital radius changed, they would shift again. The points are not fixed in absolute space. They are fixed relative to the bodies that generate them. They travel with the Earth as it orbits the Sun, always maintaining their geometric relationship to the two massive bodies, always offering the same physical conditions to anything small enough to be placed there. Webb travels with L2, Gaia travels with L2, WMAP traveled with L2, Planck traveled with L2, They orbit the L2 region in their respective halo and Lagrange paths, and L2 itself travels with Earth along Earth's orbit at 30 kilometers per second, and Earth travels around the Sun, and the Sun travels around the center of the Milky Way, and the entire solar system moves through the local group of galaxies. Everything is in motion, nothing is truly still. But the geometry of the Lagrange points persists through all of this motion, because the geometry is defined by relationships, not positions. As long as the Sun and Earth exist in their current orbital configuration, the 5 points will exist with them. And as long as the points exist, they will continue to offer what they have always offered: a location in space where the mathematics of gravity provides, for a small object, the closest thing to stability that the universe permits. The night is long, the instruments continue operating. The cold mirror at L2 is collecting photons right now. As this moment passes, ancient light from the first galaxies arriving at a golden surface and being converted into data that will be transmitted to Earth and analyzed for years. The solar wind is arriving at L1 right now, being measured by instruments that will alert space weather forecasters if a coronal mass ejection is embedded in the flow. And farther away, 60 degrees ahead of Earth in its orbit, a different kind of archive is waiting. Not data from modern instruments, not light from ancient galaxies. Something older. Material left over from the formation of the solar system itself, locked in gravitational equilibrium since before the Earth existed, preserved at the L4 and L5 points of the largest planet in the solar system. The story of those points and what lives in them continues in the dark ahead. Before moving to the Trojan asteroids of Jupiter, it is worth understanding what made L2 the specific location that transformed observational cosmology. Every major observatory deployed to L2, WMAP, Planck, Herschel, Gaia, Webb, shared a common set of design constraints that the L2 environment uniquely satisfied. These constraints were not arbitrary. They emerged from the physics of what these instruments were trying to measure. The cosmic microwave background, which WMAP and Planck were designed to map, has an average temperature of 2.725 Kelvin. The temperature variations across the sky that carry the imprint of the early universe's density structure, the fluctuations from which galaxies and galaxy clusters eventually grew, are approximately 100 microkelvin in amplitude, 100 millionths of a degree against a background of 2.725 Kelvin. Detecting this signal requires that the instrument's own thermal noise be reduced below the level of the signal being measured. At WMAP's operating temperature of approximately 90 Kelvin, the instrument noise was manageable because of the detector technology used. At Planck's operating temperature of 0.1 Kelvin, the sensitivity was sufficient to map temperature fluctuations at the level of a few microkelvin. These operating temperatures were achieved through a combination of passive cooling, the natural radiation of heat into the cold sky, and active refrigeration systems. The passive cooling component was only viable because L2's thermal environment provides a cold hemisphere, the hemisphere facing away from the Sun, that is at the temperature of deep space, approximately 2.7 Kelvin. An instrument radiating heat into this hemisphere reaches thermal equilibrium at a temperature determined by the balance between its internal heat generation and its radiative heat loss. In low Earth orbit, this balance is continuously disrupted. Earth's thermal emission at approximately 255 Kelvin heats the spacecraft on every pass. The day-night cycle, occurring every 90 minutes, causes thermal cycling that introduces noise and mechanical stress. The result is that passive cooling in low Earth orbit can achieve temperatures of perhaps 60 to 80 Kelvin for a well-shielded instrument, not cold enough for the most sensitive infrared or microwave detectors. At L2, with no Earth emission and no thermal cycling, passive cooling alone can bring a well-designed instrument to temperatures below 40 Kelvin. Active cryocoolers can then extend this to the millikelvin range with modest power budgets. This thermal advantage is compounded by the electromagnetic environment. In low Earth orbit, the Van Allen radiation belts continuously bombard spacecraft with high-energy charged particles, causing radiation damage to detectors and electronics. At L2, outside the magnetosphere, the radiation environment is less severe, dominated by galactic cosmic rays and solar energetic particles, rather than trapped radiation belt particles. This extends detector lifetimes and reduces the rate of single-event upsets in sensitive electronics. The combination of cold, dark sky, stable thermal environment, and relatively benign radiation environment makes L2 the premier location for space-based astronomy in the inner solar system. But L2 has a constraint that L1 does not face in the same way. A spacecraft at L2 is in the shadow of both the Earth and the Sun for a small fraction of its orbit around the equilibrium point. For most of the halo orbit, the spacecraft has clear solar illumination on its sun-facing side. Its solar panels generate power normally, but at certain points in the orbit, the spacecraft enters a region where Earth occults the Sun from the spacecraft's perspective, interrupting solar power generation. Mission designers typically size the halo orbit to avoid this, choosing an orbit amplitude that ensures the spacecraft never passes directly behind Earth, as seen from the Sun. Webb's halo orbit is designed with this constraint in mind. Its orbit around L2 has a period of approximately 6 months and an amplitude chosen to ensure continuous solar illumination of the sunshield's sun-facing side. The sunshield itself is a thermal engineering achievement, independent of the orbital design. 5 layers of Kapton film, each coated with aluminum and silicon on different surfaces, work together to achieve a temperature reduction from approximately 185 degrees Celsius on the sun-facing first layer to minus 233 degrees Celsius on the space-facing fifth layer. The layers are separated by gaps that allow the absorbed solar heat to radiate out the sides of the shield, rather than conducting through to the mirror side. The temperature difference across the 5-layer sunshield, from the first layer to the fifth, is approximately 300 degrees Celsius. Each layer is slightly cooler than the one before it because it receives less direct solar radiation and more reflected radiation from the previous layer. The progressive reduction in temperature across 5 layers achieves what no single layer could, a final temperature that is cold enough for the telescope's mirrors and instruments to operate. This engineering solution was only necessary because of the science being attempted, and the science was only possible because of the location, and the location was only accessible because of the orbital mechanics that Farquhar computed and ICE-3 demonstrated. The chain from 1772 to 2022, from Lagrange's equations to Webb's first images, is unbroken. It passes through Farquhar's orbital mechanics work, through the launch of ICE-3, through decades of cryogenic engineering, through the fabrication of gold-coated beryllium mirror segments, and through 29 days of transit to a point in space defined entirely by its geometry. The most powerful telescope ever built exists at a mathematical address. Every photon that Webb collects, every ancient signal from a galaxy that formed when the universe was less than 500 million years old, arrives at a mirror located at a gravitational equilibrium point that moves through space at 30 kilometers per second, following the Earth, following the Sun, following the Milky Way's rotation, following the local group's motion through the universe. The telescope is not still. The Lagrange point is not still. Nothing in the universe is still. But the geometry persists. The balance of forces that defines L2 persists, as long as the Sun and Earth orbit each other. And as long as that geometry persists, the cold, dark side of L2 will remain open, an unobstructed window into the universe, available to any instrument cold enough, sensitive enough, and precisely engineered enough to use it. Webb is using it now, and the mirror is gold, and the photons are ancient, and the universe is still answering the question of what happened at the beginning. The data is flowing back to Earth at a rate of approximately 28 gigabytes per day through the Deep Space Network. It is being processed, calibrated, and archived. Scientists around the world are analyzing it, some looking for the first galaxies, some looking for molecules in the atmospheres of exoplanets, some looking for the thermal signatures of planetary formation around young stars. At this moment, as the night deepens, the mirror is open and the detectors are counting photons. 60 degrees ahead of Earth in its orbit around the Sun, 4.5 billion years of gravitational equilibrium has produced a different kind of archive. Not images, not data, but matter itself. The solar system's most ancient objects, preserved in the amber of gravitational geometry, waiting for the first spacecraft to arrive and read them directly. The transition from L2 to the Jupiter-Trojan asteroids requires crossing almost the entire inner solar system. L2 sits 1.5 million kilometers from Earth, 4 times the distance to the Moon, a distance light crosses in 5 seconds. The Jupiter-Trojan asteroids at L4 and L5 sit approximately 5.2 astronomical units from the Sun, nearly 800 million kilometers from Earth. At closest approach, a distance light crosses in approximately 44 minutes. The scale difference between the Sun-Earth Lagrange points and the Sun-Jupiter Lagrange points reflects the scale difference between the two gravitational systems. The Sun-Earth L4 and L5 points sit approximately 1 astronomical unit from Earth along Earth's orbital path. The Sun-Jupiter L4 and L5 sit approximately 5.2 astronomical units from the Sun, 60 degrees ahead of and behind Jupiter in its 12-year orbit. Jupiter's orbital period, the time it takes to complete one orbit around the Sun, is approximately 11.86 years. The Trojan asteroids at L4 and L5 orbit the Sun with the same period, maintaining their 60-degree angular separation from Jupiter across each revolution. This is the definition of a true Trojan, an object locked in a one-to-one orbital resonance with a planet, librating around the L4 or L5 point of the planet's orbital system, sharing the planet's orbital period while never approaching the planet closely. The stability of L4 and L5 in the Sun-Jupiter system is exceptional precisely because Jupiter is massive. Jupiter contains more than twice the mass of all other planets in the solar system combined. Its mass relative to the Sun, approximately 1,000th of the solar mass, is large enough to create deep, stable L4 and L5 potential wells. The condition for stability, that the mass ratio between the primary and secondary body must exceed 24.96 to 1, is satisfied by the Sun-Jupiter system with enormous margin. The result is that objects captured at or near L4 and L5 in the early solar system have remained there for billions of years. Current estimates, based on observations from ground-based and space-based surveys, place the number of known Jupiter Trojan asteroids above 13,000, with a total estimated population, including objects too small to have been individually cataloged, potentially in the hundreds of thousands. The two Trojan swarms, L4 and L5, are of roughly comparable total mass and population, though the L4 swarm, the leading swarm, appears slightly larger in current surveys. Hundreds of thousands of objects locked in the same gravitational trap for 4.5 billion years. The Trojan asteroids are divided by astronomical convention into two camps named after characters from Homer's Iliad. The L4 swarm, the leading swarm 60 degrees ahead of Jupiter, is designated the Greek camp. The L5 swarm, the trailing swarm 60 degrees behind Jupiter, is designated the Trojan camp. Individual objects in the Greek camp are named after Greek heroes from the Trojan War: Achilles, Odysseus, Ajax. Individual objects in the Trojan camp are named after Trojan heroes: Hector, Priam, Aeneas. There is one deliberate exception to this convention. The asteroid Patroclus, a member of the Trojan camp at L5, is named for a Greek hero, and the asteroid Hector, a member of the Greek camp at L4, is named for a Trojan hero. Both were named before the naming convention was established, and both have been allowed to remain as permanent anomalies, enemy spies, as astronomers sometimes describe them, in the wrong camp. The physical properties of the Jupiter Trojan asteroids are scientifically significant, precisely because of their age. These objects formed in the outer solar system during the earliest phase of planetary formation, in the first few million years of solar system history. The current leading model of solar system formation, the NICE model and its successors, proposes that the giant planets did not form in their current orbital positions. Jupiter likely formed farther out and migrated inward, while Uranus and Neptune may have formed closer to the Sun and migrated outward. During this period of planetary migration, gravitational resonances swept through the outer solar system, scattering objects from their original orbits. The Jupiter Trojan asteroids are believed to have been captured into their L4 and L5 positions during this turbulent early period. They are not objects that formed at L4 and L5. They are objects that were swept up by the Trojan capture mechanism as Jupiter migrated and the Lagrange points moved through regions of the outer solar system that were populated with primordial material. This means the Trojan asteroids carry the chemical and physical signature of material from the outer solar system, perhaps from beyond the original location of Jupiter's formation. They are samples of the primordial solar nebula from regions of the solar system that are now largely inaccessible. Understanding their composition provides constraints on the conditions in the outer protoplanetary disk during the first few million years of solar system history. Ground-based spectroscopy of Jupiter Trojan asteroids has established that they have very low albedo. They reflect only about 4 to 7% of incident sunlight, making them among the darkest objects in the solar system. Their spectra suggest surfaces rich in carbonaceous material, complex organic compounds, possibly including the amino acid precursors that are found in carbonaceous chondrite meteorites. But ground-based observations cannot definitively characterize the surface composition or internal structure of individual objects. This is what the Lucy mission was designed to address. Lucy launched on October 16, 2021, the same year as Webb, a remarkable coincidence that placed two landmark NASA missions in transit simultaneously, where Webb headed for L2 to look outward at the universe. Lucy headed into the outer solar system to examine the solar system's own ancient material. Lucy's mission profile is among the most ambitious trajectory designs in planetary exploration history. Over a 12-year primary mission, the spacecraft will execute a series of gravity assist maneuvers, using the gravitational fields of Earth and Jupiter to reshape its trajectory without expending propellant, that will allow it to visit 7 Trojan asteroids across both the L4 and L5 swarms, plus 1 main belt asteroid with a single spacecraft and a single launch. The trajectory is possible because of the specific geometry of the Trojan swarms and the timing of their positions relative to Earth during the mission window. Lucy will swing past Earth 3 times during its mission in October 2022, December 2024, and December 2030, using each Earth flyby to adjust its velocity and trajectory. It will visit 4 asteroids in the Greek L4 swarm on its outbound journey, then return to the inner solar system for a final Earth gravity assist, then cross to the Trojan L5 swarm to visit the Patroclus-Menoetius binary. The binary nature of Patroclus-Menoetius, 2 objects of comparable size, approximately 140 and 113 kilometers in diameter respectively, orbiting each other, makes it a scientifically unique target. Binary systems preserve information about the collision history and physical properties of their components that single objects do not. The mutual orbit of the 2 components can be used to determine their total mass. Combined with volume measurements from flyby imaging, this gives the bulk density, which constrains the internal composition and porosity of the objects. Lucy's instruments include cameras, a thermal emission spectrometer, and a high-gain antenna for radio science. The radio science investigation uses precise measurements of the Doppler shift of radio signals transmitted between Lucy and Earth to determine the masses of the target asteroids, the same technique used by Cassini to measure the masses of Saturn's moons. The first Trojan asteroid encounter, Euripides and its small satellite Ceuta, occurred in August 2027. Subsequent encounters continue through the primary mission. The flyby velocities are high, several kilometers per second relative to the target, meaning each encounter lasts only a few hours of closest approach. But the instruments are sensitive, and the data returned from each flyby will take months to fully analyze. What Lucy finds will not change the fundamental understanding that the Trojan asteroids are primordial, that is already established. What it may change is the level of detail in that understanding, the specific organic compounds present, the distribution of ice within the objects, the evidence for or against catastrophic collisions, the precise orbital histories that can be reconstructed from the physical characteristics of the objects themselves. The Trojan asteroids at L4 and L5 are not merely interesting objects, they are the oldest accessible material in the solar system, preserved in gravitational equilibrium since before the Earth's oceans formed, since before the late heavy bombardment, since before life appeared on this planet. They have been waiting at L4 and L5 for 4.5 billion years. Lucy is the first visitor. Lucy is not traveling to an empty region of space. When it reaches the Greek camp at L4 and later the Trojan camp at L5, it will be flying through a swarm, a population of objects spread across a region of the solar system, roughly comparable in extent to the asteroid belt, occupying an arc of Jupiter's orbit, spanning tens of degrees on either side of the exact L4 and L5 points. The Trojan swarms are not densely packed. The average distance between objects in the Trojan cloud is millions of kilometers. Lucy will not navigate through a field of close objects. It will approach individual targets across the void, spending most of its transit time in the near-empty space between objects that can barely be detected from Earth. But the swarm's statistical density is scientifically meaningful. The fact that hundreds of thousands of objects have remained in these gravitational basins for 4.5 billion years tells a story about the dynamical history of the outer solar system that could not be told any other way. The Nice model, named for the city of Nice in France, where it was developed in 2005 by a team including Alessandro Morbidelli, Hal Levison, Cleomenes Tsiganis, and Rodney Gomes, proposes a specific sequence of events in the early solar system that explains several otherwise puzzling features of the current solar system architecture. In the Nice model, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, initially formed in a more compact configuration, all within approximately 15 to 17 astronomical units of the Sun. Beyond their orbits lay a vast disk of planetesimals, small rocky and icy bodies, the leftover building material from the planet formation process. This disk extended from just beyond the outermost giant planet to perhaps 35 or 40 astronomical units from the Sun. The giant planets interacted gravitationally with this disk over hundreds of millions of years. Planetesimals scattered by the planets gained and lost orbital energy, causing a slow migration of the planetary orbits. Jupiter migrated slightly inward, Saturn migrated outward. Eventually, Jupiter and Saturn crossed a 2-to-1 mean motion resonance, a configuration in which Jupiter completes exactly 2 orbits for every 1 orbit of Saturn. This resonance crossing was catastrophic for the outer solar system. The gravitational coupling between Jupiter and Saturn in this resonance destabilized the orbits of Uranus and Neptune, driving them outward onto highly eccentric trajectories. These eccentric giant planet orbits then swept through the primordial planet-seminal disk, scattering planet-seminoles throughout the solar system. Objects were sent into the inner solar system, explaining the late heavy bombardment, the period approximately 3.9 billion years ago, when the moon's cratered surface accumulated most of its large impact basins. Objects were scattered outward to form the Kuiper Belt and the Oort cloud, and some objects were captured into the Trojan regions at L4 and L5 of Jupiter as the giant planets settled into their current orbits. The craters on the moon record an event that also filled Jupiter's Trojan points. The Nice model has been refined and debated since its publication. Alternative proposals, the Grand Tack and Jumping Jupiter models, differ in timing and sequence, but across all of them, the Trojan asteroids are understood as material captured during a period of giant planet orbital instability, their population reflecting the efficiency of that ancient capture event. Understanding the composition, size distribution, and physical properties of the Trojans therefore provides observational constraints on the models of solar system formation. If Lucy finds that the Trojans are compositionally similar to Kuiper Belt objects, the distant icy bodies beyond Neptune, it would support models in which the Trojans originated in the outer solar system beyond Jupiter's original formation location. If it finds properties more consistent with objects from the region between Jupiter and Saturn, it would point toward a different capture scenario. The compositional comparison between the Trojan asteroids and other small body populations is one of the central scientific questions of the Lucy mission. The low albedo and reddish spectral slope of many Trojan asteroids resembles, and in some cases matches, the spectral properties of ultra-red Kuiper Belt objects, which have the most extreme red colors of any known solar system objects. These ultra-red colors are attributed to complex organic compounds formed by radiation processing of ices over billions of years. If some Trojan asteroids have the same spectral properties as Kuiper Belt objects, it suggests a common origin in the cold outer solar system, far from the Sun, where icy materials and radiation processing dominated the surface chemistry. This connection between the Trojan asteroids and the Kuiper Belt, mediated by the dynamical chaos of the early solar system, is one of the most striking predictions of the modern models of solar system formation. Objects that now orbit at 5 astronomical units, trapped at L4 and L5, may have formed at 20 or 30 astronomical units and been delivered to their current positions by the gravitational chaos that accompanied the giant planet's migration. The Lagrange points did not create these objects, but they preserved them. Without the gravitational stability of L4 and L5, the primordial material captured during the early solar system instability would have been gradually scattered, slowly perturbed by gravitational interactions with Jupiter and the other planets until it was removed from the region entirely. The stability of the Trojan points converted what would have been a temporary population into a permanent archive. The word archive is not metaphorical. The Trojan asteroids are a physical record. Their surfaces record the history of solar radiation processing, the gradual chemical modification of organic compounds by ultraviolet and charged particle radiation over 4.5 billion years. Their bulk compositions record the chemistry of the outer solar nebula at the time of their formation. Their size distributions record the collisional history of the swarm. How many objects have been broken apart by impacts? How many have accreted smaller material? How the population has evolved. Reading this record requires visiting the objects in situ. Remote observations from Earth can characterize their surfaces crudely, but cannot penetrate the surface to sample the interior composition, cannot resolve the small-scale structures that record impact history, and cannot measure the masses and densities of individual objects without the radio science that only a close flyby makes possible. Lucy will not land on any of its target asteroids. Its flyby velocities are too high, and its trajectory is too constrained. Each encounter will last a few hours of close observation, capturing imagery at resolutions down to approximately 10 meters per pixel, collecting thermal infrared spectra to characterize surface composition, and performing radio science to measure masses. In those few hours per target, Lucy will collect more data on each object than all previous Earth-based observations combined. Between encounters, the spacecraft travels in the near silence of the outer solar system, propelled by its 2 circular solar arrays, each approximately 3.5 meters in diameter, mounted like wings on either side of the spacecraft body. The solar panels were sized for operation at Jupiter's distance, where the solar flux is approximately 25 times weaker than at Earth. At those distances, generating adequate power requires large collection areas. The distinctive twin panel design gives Lucy an instantly recognizable profile. During one of its Earth gravity assist maneuvers, ground teams discovered that one of the solar panels had not fully latched in the fully deployed position. The panel was approximately 75 to 95% deployed, not fully latched, but generating near full power. After assessment, mission managers determined that the spacecraft could continue its mission safely with the panel in its current state. The latch issue did not alter the trajectory or the science plan. The mission continued. The trajectory held. The archive is still waiting. The Earth-Moon system has its own set of Lagrange points, smaller in scale but closer in distance. The Earth-Moon L1 sits approximately 58,000 kilometers from the Moon on the near side, between Earth and the Moon. The Earth-Moon L2 sits approximately 65,000 kilometers from the Moon on the far side. The Earth-Moon Lagrange points are less stable than the Sun-Earth points because the mass ratio between Earth and Moon, approximately 81:1, is smaller than the mass ratio between the Sun and Earth, approximately 333,000:1. The smaller mass ratio means the L4 and L5 points of the Earth-Moon system are only marginally stable, near but below the stability threshold, and objects placed there experience more perturbation from the Sun's gravity than the Jupiter-Trojan asteroids experience. Despite this marginal stability, observations have suggested the possible existence of material at Earth-Moon L4 and L5. In 1961, the Polish astronomer Kazimierz Kordylewski reported observing faint dust clouds at the Earth-Moon L4 and L5 positions. These became known as Kordylewski clouds. Their existence was debated for decades. The dust, if present, would be extremely diffuse and difficult to distinguish from the general zodiacal light background. In 2018, a team of Hungarian researchers reported new observations using polarimetric imaging, a technique that measures the polarization of scattered light, that appeared to confirm the presence of dust concentrations at the Earth-Moon L4 and L5 positions. Their analysis suggested the clouds were real, approximately 4 times the size of the full moon in angular extent, consisting of dust particles scattering sunlight at a level slightly above the local zodiacal background. The Kordylewski clouds, if confirmed, would represent the Earth-Moon system's equivalent of the Jupiter-Trojan asteroids, material loosely trapped at the gravitational equilibrium points of the Earth-Moon system. Unlike the Jupiter-Trojans, which are large solid bodies with well-measured orbits, the Kordylewski clouds would be diffuse assemblages of dust particles, continually replenished by interplanetary dust infall and gradually depleted by radiation pressure and gravitational perturbations. The existence of dust at Earth-Moon L4 and L5 is consistent with the physics. The Earth-Moon L4 and L5 points are not strongly stable, but they are locally stable enough to accumulate material on timescales of months to years. A continuous source of interplanetary dust drifting through these regions would result in a statistical excess of dust near the equilibrium points, not a permanent trapped population like the Jupiter-Trojans, but a time-averaged concentration. The Earth-Moon Lagrange points have also attracted attention as potential locations for future human infrastructure in cislunar space. The Lunar Gateway, NASA's planned small space station in lunar orbit, developed as part of the Artemis program, is not being placed at an exact Lagrange point. It will orbit in a near rectilinear halo orbit, a specific orbital family that exists in the vicinity of the Earth-Moon L2 region. The near rectilinear halo orbit provides continuous communication with Earth, reasonable access to the lunar surface, and a relatively stable orbit, requiring modest station-keeping fuel. The selection of a near rectilinear halo orbit for the Gateway reflects the same logic that drove the selection of halo orbits around Sun-Earth L1 and L2 for solar and astronomical observatories. The exact Lagrange point cannot be occupied stably. The halo orbit family in the vicinity of the equilibrium point provides a workable alternative, an orbit that maintains approximate proximity to the equilibrium geometry while being practically achievable and sustainable. The Gateway will serve as a staging point for lunar surface missions, and eventually as a way station for missions beyond the Moon. Its position in the Earth-Moon L2 vicinity gives it access to both the near side and far side of the Moon, making it geometrically useful for missions to multiple lunar destinations. The use of the Earth-Moon L2 region for crewed infrastructure represents a new phase in the operational use of Lagrange points, one that Lagrange could not have imagined in 1772, that Farquhar could only theorize about in the 1960s, and that is now actively being designed and built. The progression is remarkable. L1 became a solar wind monitoring station. L2 became an astronomical observatory platform. Now the Earth-Moon L2 vicinity is becoming a staging base for human exploration of the lunar surface. And the mathematics underlying all of it is the same mathematics that Lagrange published in a paper on the three-body problem more than 250 years ago. The solar system's Lagrange points are not just locations for scientific instruments, they are increasingly recognized as strategic nodes in the architecture of human activity beyond Earth. The fuel efficiency they provide, the ability to maintain a position with minimal propellant expenditure, translates directly into mission cost, mission duration, and operational flexibility. Understanding the full network of Lagrange points in the solar system, not just Sun-Earth and Earth-Moon, but Sun-Mars, Sun-Jupiter, and beyond, is part of the long-term planning for interplanetary exploration that is beginning to take shape in mission concept studies and trajectory analyses around the world. That network and the hidden highways connecting it is the subject that the night will continue to explore. The concept of Lagrange points as nodes in a larger transportation network is one of the more recent and transformative ideas in orbital mechanics. For most of the history of spaceflight, mission trajectories were designed using the two-body approximation, treating the Sun and a single planet as the only relevant gravitational influences, and designing trajectories as sequences of conic sections, Hohmann transfers, and gravity assists. This approach works well for many mission types, particularly when the goal is to travel between two well-separated bodies on a reasonable timeline. But the two-body approximation misses something. In the real solar system, every spacecraft is always subject to the gravitational influence of multiple bodies simultaneously. Near Earth, the Moon's gravity matters. Near Jupiter, the Galilean moons matter. In the space between planets, the combined gravitational fields of the Sun and multiple planets create a landscape of gravitational hills, valleys, and ridges that is far more complex than the two-body picture suggests. In this complex landscape, there are regions of very low gravitational gradient, regions where the net force on a spacecraft changes very slowly with position. These low gradient regions are associated with the Lagrange points and with the manifolds, mathematical surfaces in phase space that emanate from the unstable Lagrange points in a way that connects them. The key insight is that L1 and L2 are saddle points in the gravitational potential. The instability of a saddle point means that there are specific directions in phase space along which the spacecraft will naturally flow away from the point. These directions are called the unstable manifolds of the saddle point. Conversely, there are specific directions along which a spacecraft approaching from a distance will naturally flow toward the saddle point. These are the stable manifolds. The stable and unstable manifolds of Lagrange points form tube-like structures in phase space, long curved tubes that connect Lagrange points across immense distances of the solar system. A spacecraft placed on the stable manifold of a Lagrange point will naturally flow toward that point with no propulsion required. A spacecraft ejected along the unstable manifold will naturally flow away from the point, following the manifold tube to a distant destination. This network of manifold tubes has been called the Interplanetary Transport Network. The concept was developed in the 1990s and early 2000s by a group of researchers including Martin Lowe, Shane Ross, and Gerald Marsden. They demonstrated through numerical computation of the restricted three-body problem in various sun-planet and planet-moon systems that the manifold tubes of different Lagrange points can intersect, creating low-energy pathways between different parts of the solar system that require far less propellant than conventional Hohmann transfers. A spacecraft traveling along the Interplanetary Transport Network does not follow the smooth, elegant ellipses of the two-body approximation. Its path is complex, multi-lobed, and slow. It may take years or decades to travel distances that a conventional trajectory would cover in months. But the propellant requirement is dramatically lower, in some cases approaching zero for certain transfers, given the right initial conditions. The practical limitations are significant. The slow travel time makes the network unsuitable for human missions or time-sensitive science missions. The complex trajectories require extremely precise navigation, and the energy savings are only available at specific times. The manifold tubes move as the planets move, and the intersections between them occur at specific geometrical configurations that repeat on timescales of years. Despite these limitations, the network is real and has been operationally used. The Genesis mission, launched in August 2001, was designed to collect samples of solar wind, the stream of charged particles emitted by the sun, and return them to Earth. Mission designers, including Martin Lowe, used a trajectory that exploited the manifold structure of the Sun-Earth L1 and L2 points to design a path that traveled to the vicinity of L1, looped around both L1 and L2, and then returned to Earth, all with a much lower propellant budget than a conventional trajectory would have required. The Genesis trajectory was not a straight line or a simple ellipse. It was a complex figure-8-like path that spent more than 2 years in the vicinity of the Sun-Earth Lagrange points before returning the sample capsule to Earth in September 2004. The spacecraft followed a river in the mathematics of gravity that no human eye can see. The sample return capsule entered Earth's atmosphere over the Utah desert as planned. The drogue parachute deployed. The main parachute, however, failed to deploy. The capsule impacted the desert floor at approximately 310 kilometers per hour, cracking open and contaminating a portion of the sample with Utah soil. Despite the hard landing, a significant fraction of the solar wind samples were recovered from the collector arrays inside the capsule. The science was salvaged. The results from the Genesis samples, measurements of the isotopic composition of solar wind particles, have been published in numerous papers, providing new constraints on the composition of the early solar nebula and the processes by which the sun formed. The mission's trajectory design demonstrated the operational reality of the interplanetary transport network. The manifold tubes are not merely theoretical constructs. They are dynamical highways that can be planned, targeted, and followed by actual spacecraft with actual propulsion systems and actual navigation errors. Future missions to the outer solar system may make more extensive use of the network. A mission to Jupiter's Trojan asteroids at L4 and L5, beyond Lucy's trajectory, might use Lagrange point manifolds to reduce the propellant cost of orbit insertion at the target. A mission to the moons of Jupiter might use the manifold connections between the L1 and L2 points of the different Galilean moon systems to hop between moons with minimal fuel expenditure. This approach to interplanetary travel, slow, complex, but fuel efficient, is sometimes called ballistic lunar or interplanetary transfer. It treats the solar system not as a collection of objects separated by empty space, but as a structured gravitational landscape in which certain paths exist naturally, requiring less energy to follow than the straight-line intuition of Newtonian mechanics would suggest. Jupiter is not the only planet with Trojan asteroids. The discovery and cataloging of Trojan asteroids at other planets has expanded the known inventory of gravitationally trapped material throughout the solar system. Mars has a small Trojan population. As of 2024, 9 confirmed Mars Trojan asteroids are known, 5 at Mars L4 and 4 at Mars L5. The Mars Trojans are compositionally diverse, suggesting they were captured from different source populations during the early solar system instability. Their small numbers compared to Jupiter's swarm of thousands reflect Mars's much smaller mass and correspondingly shallower Trojan stability wells. Neptune has a growing catalog of known Trojan asteroids, more than 20 confirmed as of recent surveys, with estimates suggesting thousands more await discovery. The Neptune Trojans are particularly interesting because Neptune's current orbital location, approximately 30 astronomical units from the Sun, places them in the outer solar system, where primordial icy material is expected to have been abundant. Neptune's Trojans may be compositionally similar to Kuiper Belt objects and could provide insights into the outer solar system's primordial chemistry, comparable to what Jupiter's Trojans offer for the intermediate solar system. Earth itself was confirmed to have at least one Trojan asteroid, 2010 TK7, discovered in 2010 by the Wide Field Infrared Survey Explorer. This object, approximately 300 meters in diameter, orbits the Sun at Earth's orbital distance, librating around the Sun-Earth L4 point. Its orbit is dynamically stable on timescales of thousands of years, though numerical simulations suggest it will eventually escape the Trojan region. Other Earth Trojan candidates have been identified, though the geometry of Earth's orbit makes them difficult to observe. They are located near the Sun as seen from Earth, making ground-based observation challenging. The Venus system has produced a confirmed Trojan candidate as well, 524522 Zoroaster, a small object librating around the Sun-Venus L4 point. Uranus has at least one confirmed Trojan. The Trojan populations of the outer planets are still being systematically surveyed as telescope technology improves and sky coverage of the difficult observational regions near the Sun increases. The picture that emerges from these discoveries is of a solar system that is, in a meaningful sense, full. Not full of large objects. The space between planets is overwhelmingly empty by any reasonable definition, but full of structure, full of gravitational geometry that organizes matter into specific patterns that persist over geological timescales. The Lagrange points and their associated dynamical features, halo orbits, Lissajous orbits, manifold tubes, Trojan swarms, are not curiosities confined to the Sun-Earth or Sun-Jupiter system. They are universal features of every gravitationally bound two-body system in the solar system. Every planet has them. Every large moon has them around its planet. Every binary asteroid system has them. The solar system is threaded with this structure from the inner planets to the outer reaches of the Kuiper Belt. The solar system is not empty space between islands of matter. It is a map drawn in gravity. The night continues, the numbers are large, and the distances are immense. Jupiter's Trojans orbit 5 times farther from the Sun than Earth. Neptune's Trojans orbit 30 times farther. The Kuiper Belt extends to 50 astronomical units and beyond. The Oort cloud, from which comets occasionally fall inward, extends perhaps 100,000 astronomical units, nearly halfway to the nearest star. At all of these scales, the same mathematics applies. The same 5 Lagrange points exist in every two-body system. The same manifold structures connect them. The same physical conditions, gravitational equilibrium, thermal extremes, ancient material, exist at each scale and distance. Lagrange did not know any of this in 1772. He was solving an abstract mathematical problem. The solar system he lived in was not yet mapped beyond Saturn. The existence of asteroids was unknown. The concept of a spacecraft was centuries away. But the mathematics he found was the mathematics of the universe, and the universe had already arranged itself according to it, long before anyone looked. The Lagrange points were there when the solar system formed. They were there when the first trilobites appeared in Earth's oceans. They were there when the first humanids looked up at the night sky. They were there, filled with the same ancient material, when Lagrange wrote his equations. They are there now, in the dark above, unchanged. And in those dark regions between the planets, in the gravitational basins that Lagrange's mathematics defines, the solar system's oldest material waits, cold, unchanged, patient beyond any human scale of time. The night deepens, the pace of the universe is slow, and the silence between objects is vast, and in that silence the geometry of gravity persists, ordering the motion of everything, offering its 5 still points to anything small enough to rest there. The solar system does not end at Neptune. Neptune orbits the Sun at approximately 30 astronomical units, 30 times the Earth-Sun distance, roughly 4.5 billion kilometers from the Sun. Light takes approximately 4 hours and 10 minutes to travel from the Sun to Neptune. A spacecraft traveling at the speed of Voyager 2, which reached Neptune in 1989, after a 12-year journey, would require another 12 years to double Neptune's orbital distance. Beyond Neptune, the solar system continues. The Kuiper Belt extends from approximately 30 to 50 astronomical units. The scattered disk, a dynamically excited population of icy objects with highly elliptical orbits, extends farther. The Oort cloud, a spherical reservoir of cometary nuclei, may extend from a few thousand to 100,000 astronomical units from the Sun. At all of these distances, the same gravitational geometry applies. Every planet in the solar system generates 5 Lagrange points in its orbital relationship with the Sun. Every large moon generates 5 Lagrange points in its relationship with its parent planet. The number of Lagrange point systems in the solar system is not 5. It is in the hundreds. Neptune has Trojan asteroids at its L4 and L5 points. More than 20 have been confirmed as of recent surveys, with theoretical models suggesting the actual population may be comparable in number to Jupiter's Trojan swarm, potentially thousands of objects awaiting discovery. Neptune's Trojans were captured during the same period of giant planet migration that populated Jupiter's Trojan regions, and their compositions are expected to reflect the cold outer solar system chemistry of the primordial trans-Neptunian disk. Observing Neptune's Trojans is technically challenging. At 30 astronomical units, they receive approximately 900 times less sunlight than objects at Earth's distance. Their reflected light is faint, their angular velocity across the sky is slow, and their positions near the opposition point of a planet that takes 165 years to complete one orbit means that systematic surveys require patience and large aperture telescopes. The Vera the 100th Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, began its legacy survey of space and time in 2025. This survey will systematically image the entire accessible sky every few nights, building a catalog of moving objects in the solar system that will expand the known population of small bodies by orders of magnitude. Neptune's Trojans, Mars's Trojans, and potentially Earth's Trojans will all benefit from this survey, as will the broader population of Kuiper Belt objects and scattered disk objects. The Rubin Observatory's contribution to the inventory of Lagrange point populations is expected to be transformative. Current estimates of Neptune's Trojan population are based on extrapolations from a small number of detected objects. The Rubin survey will detect hundreds or thousands of Neptune Trojans directly, allowing the size distribution, color distribution, and orbital characteristics of the population to be measured statistically rather than inferred. The solar system's hidden populations are about to be counted for the first time. The Mars Trojan asteroids represent a smaller but scientifically interesting population. 9 confirmed Mars Trojans are known, 5 at the Sun-Mars L4 point and 4 at the Sun-Mars L5 point. Their orbits are stable on timescales of millions of years, though Mars's smaller mass produces a narrower stability region and less efficient long-term retention. The largest known Mars Trojan is 5,261 Eureka, approximately 2 kilometers in diameter, discovered in 1990. Spectroscopic observations of Eureka have identified it as an olivine-rich object, a composition that is unusual among small solar system bodies, and may represent mantle material excavated from a differentiated parent body during a large impact event. If Eureka is a fragment of ancient planetary mantle, it preserves mineralogical information about the differentiation processes of the early solar system that are otherwise inaccessible. Mars's Trojan swarm is too small to provide the statistical compositional sampling that Jupiter's swarm offers, but the individual objects are close enough. Mars reaches perihelion at approximately 1.38 astronomical units from the Sun, and its Trojans orbit at the same distance, to be studied with current instrumentation at relatively high resolution compared to Jupiter's distant Trojans. The comparison between the Mars and Jupiter Trojan populations, their compositions, size distributions, and orbital stability characteristics provides constraints on the different capture and retention efficiencies of the two systems as a function of the host planet's mass. This comparative study is part of the broader project of understanding how Lagrange point populations reflect the formation history of their host planetary systems. Uranus has at least one confirmed Trojan, 2011 QF99, a roughly 60-kilometer object discovered in 2011. Its orbital stability has been studied through numerical simulation, with results suggesting it is currently in a temporary Trojan configuration and will escape within approximately 1 million years. Whether it was captured recently or has been in a marginally stable configuration for much longer is not yet established. The Uranus system is poorly characterized overall. No spacecraft has visited Uranus since Voyager 2's brief flyby in January 1986, the only close observation of the planet in history. A Uranus orbiter mission has been identified as the highest priority large mission in the 2023 to 2032 Planetary Science Decadal Survey. Such a mission, if developed and launched in the early 2030s, would arrive at Uranus in the early to mid-2040s and would provide the first detailed characterization of the Uranian system since Voyager 2. A Uranus orbiter mission would naturally survey the Uranian Trojan population as part of its broader characterization of the outer solar system environment around Uranus. Whether a single confirmed Trojan implies a larger undiscovered population, or whether the Uranian Trojans are genuinely sparse, is one of the many open questions about this understudied system. Venus also has a confirmed Trojan. The object 524522 Zoroaster was confirmed as a Venus Trojan in 2013. Occupying a position near the Sun-Venus L4 point. Its diameter is estimated at approximately 1 kilometer. The Venus Trojan population is even harder to survey than Earth's Trojans because Venus is closer to the Sun than Earth, placing its L4 and L5 points in regions of sky that are difficult to observe from Earth-based telescopes due to solar proximity. The existence of Trojan asteroids at Venus, Earth, Mars, Jupiter, Uranus, and Neptune demonstrates that the phenomenon of Trojan capture is not a special feature of any single planetary system. It is a generic outcome of the gravitational dynamics of the solar system that occurs wherever a planet is massive enough and has occupied its orbital position long enough to accumulate objects at its Lagrange points. The solar system is, in a physically precise sense, a system of interconnected gravitational basins. Each planet creates 5 equilibrium points in its orbital relationship with the Sun. Each of these points is connected to the others through the manifold structure of the restricted three-body problem, the low-energy pathways of the interplanetary transport network. Objects can, over long timescales, transition between different Trojan populations and between Trojan populations and other dynamical reservoirs through sequences of weak gravitational perturbations that gradually shift their orbits from one basin to another. The Jupiter Trojans occasionally eject members. Perturbations from Saturn and other planets can push Trojan asteroids to orbits that are no longer within the stability region, causing them to escape. Some of these escaped Trojans become Jupiter family comets, short-period comets with orbits that bring them into the inner solar system. Others become near-Earth asteroids, eventually crossing Earth's orbit. The material that passes through the Trojan regions is not permanently sequestered there. It circulates on very long timescales through the solar system's dynamical reservoir. The Trojan asteroids are not prisoners. They are temporary residents in a house that gravity built. This circulation connects the Trojan populations to the broader question of how organic material was delivered to the early Earth. The carbonaceous chondrite meteorites, a class of primitive meteorites with compositions that include complex organic compounds, amino acid precursors, and hydrated silicate minerals, are believed to originate primarily from the outer asteroid belt and potentially from the primordial outer solar system. The Jupiter Trojans, with their low albedo and carbonaceous spectral properties, may represent material from the same reservoir as the carbonaceous chondrites, delivered to the asteroid belt region through the dynamical processes that populated the Trojan swarms and ejected material from them. If the Trojan asteroids are compositionally similar to the parent bodies of carbonaceous chondrites, then the dynamical process that formed Jupiter's Trojan swarm, the capture of primordial outer solar system material during the giant planet migration instability, was also the process that ultimately seeded the asteroid belt with the organic-rich material that was later delivered to the early Earth by impacts. The Lagrange points, in this interpretation, are not merely gravitational curiosities. They are nodes in the delivery network for the chemical precursors of life. Lucy's compositional measurements of the Jupiter Trojans will test this connection directly. If the objects Lucy visits have the same organic inventory as carbonaceous chondrites, the chain from L4 and L5 to the chemistry of life on Earth is confirmed. If they are compositionally different, the origin of the carbonaceous chondrite parent bodies remains uncertain. The question will not be fully resolved by Lucy alone, but Lucy will provide the first in situ compositional data for these objects, and that data will constrain the models in ways that ground-based spectroscopy cannot. The night is at its deepest now. The distances that have been described, from L1's 1.5 million kilometers to Neptune's 4.5 billion kilometers to the Oort cloud's potential 100,000 astronomical units, span more than 7 orders of magnitude. The physics that operates at all of these scales is the same physics. The same gravitational equations that describe the halo orbit of Webb around the Sun-Earth L2 also describe the libration of a Neptune Trojan around the Sun-Neptune L4. The mathematics is scale invariant. This scale invariance is one of the profound features of gravity. Unlike electromagnetism, which is screened at large distances by the separation of positive and negative charges, gravity has no screening mechanism. It operates identically at 1 meter and at 1 light year, following the same inverse square dependence on distance, generating the same 5 Lagrange points in every two-body system regardless of the masses or distances involved. The Lagrange points of a neutron star binary system, or 2 stellar remnants, each containing more mass than the Sun, orbit each other at a separation of a few hundred kilometers, obey exactly the same equations as the Lagrange points of Jupiter and a tiny Trojan asteroid. The geometry is identical. The stability conditions are identical. The manifold structure is identical. The universe applies its mathematics consistently. Lagrange found a solution to a restricted version of a problem that cannot be fully solved. He found it by looking for special cases, configurations where the complexity of the general problem collapses into something tractable. The 5 equilibrium points are the special cases. They are the places where the chaos of 3 mutually interacting gravitational fields resolves into something stable, or at least approximately stable. They are the exceptions to chaos. And the solar system, 4.5 billion years old, has been filing objects into these exceptions since the beginning, slowly, through the stochastic processes of gravitational capture and orbital migration, populating the equilibrium basins with the raw material of a solar system that did not know it was building an archive. The archive is still being built. Every new Trojan asteroid discovered by the Rubin Observatory is a new entry. Every Lucy flyby is a new chapter read. Every spectrum taken of a Jupiter Trojan from a ground-based telescope is a partial translation of a document written in the chemistry of the early solar system. The reading will take a long time. The solar system is patient. The interplanetary transport network extends further into the operational history of spaceflight than the Genesis mission alone. The river analogy holds across multiple examples. Water follows the path of least gravitational resistance. A spacecraft entering a manifold tube is carried by the geometry of the solar system from one region to another at minimal propellant cost, the trade-off being time. The analogy that has been used is that of river systems. Water flowing downhill follows the path of least resistance. In a gravitational landscape, the manifold tubes are the paths of least resistance, the channels along which a spacecraft with minimal propulsion can be carried by the gravitational geometry of the solar system from one region to another. A spacecraft that enters a manifold tube near Earth's L2 point will, if it follows the tube passively, eventually approach the manifold structure of another planet's Lagrange point system. The transit may take years or decades, but the propellant cost of the transfer can be dramatically lower than a conventional Hohmann transfer. The practical application of this insight has been limited to specific mission types, those where long transfer times are acceptable and propellant mass is at a premium. The Genesis mission, as described earlier, used manifold-based trajectory design to achieve its sample return mission. The Artemis mission, which repurposed 2 Themis spacecraft that had completed their primary science mission in Earth orbit, used a remarkably complex low-energy trajectory that included passages through the Earth-Moon L1 and L2 regions and the Sun-Earth L1 region before placing the spacecraft in stable lunar orbits. The Artemis trajectory was designed precisely because the spacecraft had limited remaining propellant. The low-energy route was the only viable option. The Artemis trajectory is remarkable as an example of opportunistic mission design. 2 spacecraft, built for a different purpose, with limited fuel reserves, were given new missions by exploiting the gravitational geometry of the Lagrange point manifold network. They traveled from near-Earth space to lunar orbit by following a path that no spacecraft had previously attempted, guided by the same mathematics that Lagrange discovered in 1772. The trajectory took approximately 8 months, where a conventional transfer to lunar orbit takes approximately 3 days, but the fuel cost was within the available reserves, and both spacecraft successfully entered lunar orbit and completed a new science mission studying the lunar magnetosphere. The mathematics provided a way where there appeared to be none. The future development of cislunar space, the region between Earth and the Moon, that is now the focus of NASA's Artemis program, ESA's lunar exploration plans, and multiple commercial ventures, will make increasing use of the Earth-Moon Lagrange Point regions. The near rectilinear halo orbit planned for the Lunar Gateway is one example, but the Lagrange Point regions of the Earth-Moon system also offer natural waypoints for cargo delivery, refueling depots, and communication relay infrastructure. The Earth-Moon L1 point, located between Earth and Moon, is geometrically central to cislunar operations. A spacecraft at Earth-Moon L1 can reach either the Earth or the Moon with relatively modest propulsion, making it a natural candidate for a propellant depot or logistics hub. The development of cislunar infrastructure over the coming decades will gradually transform the Earth-Moon Lagrange points from mathematical abstractions used by mission designers into operationally familiar locations, as familiar eventually as low Earth orbit is today. The L5 Society, a space advocacy organization founded in 1975 by Keith and Carolyn Henson, inspired by the physicist Gerard K. O'Neill's work on space colonization, took its name from the Sun-Earth L5 point. O'Neill had proposed in a 1974 paper in the journal Physics Today, and more extensively in his 1977 book The High Frontier, that the Sun-Earth L5 point was an ideal location for large human space habitats. O'Neill's concept, the O'Neill cylinder, envisioned a pair of counter-rotating cylindrical structures, each approximately 8 kilometers in diameter and 32 kilometers long, placed at Sun-Earth L5. Rotation would provide artificial gravity on the inner surface. Solar energy would be collected and converted to power. The habitats would be self-sufficient in food production through controlled agricultural sections. The population of a mature habitat could number in the tens of thousands. The Sun-Earth L5 point was chosen for its gravitational stability. Objects at L4 and L5 are in stable equilibrium and would not drift away over time, and for its position along Earth's orbital path, which provides continuous access to solar energy and relatively easy communication with Earth. O'Neill's vision was not realized. The technological and economic barriers to constructing a kilometer-scale structure in space proved insurmountable for the late 20th century, but the L5 Society generated significant public interest in space colonization and directly contributed to the political and scientific culture that supported subsequent developments in space exploration and commercial spaceflight. The specific choice of L5 as the proposed habitat location was not arbitrary. It reflected a genuine understanding of the gravitational dynamics of the Lagrange points, the distinction between the stable L4 and L5 points, and the unstable L1 and L2 points, and the implication of that stability for long-duration human habitation. O'Neill's cylinders remain speculative, but the underlying gravitational reasoning was sound, and as the cost of access to space decreases and the capability to operate at large scales in cislunar space increases, the Lagrange points of the Earth-Moon and Sun-Earth systems will remain on the list of candidate locations for future infrastructure. Consider what a spacecraft at Sun-Earth L4 would actually experience. No mission has ever been sent there deliberately for science. The point sits approximately 1 astronomical unit from Earth, along Earth's orbital path, trailing 60 degrees behind the planet, sharing its orbital period, following the same arc around the Sun. From L4, the Earth would appear as a bright star in the sky, roughly as bright as Venus appears from Earth's surface. The Sun would sit at the same angular distance it always has, but the geometry of the sky would be subtly different from anything seen from Earth or any current spacecraft. At L4, the full disk of the Milky Way would be visible without the brightness gradient caused by proximity to the Sun. The zodiacal light, sunlight scattered by interplanetary dust along the orbital plane, would appear in a different distribution than it does from Earth, because the dust population at L4 may be slightly enhanced by Kordylewski-type accumulation. A sensitive photometer at Sun-Earth L4 could measure this enhancement directly, distinguishing the background zodiacal cloud from any trapped concentration at the equilibrium point itself. The thermal environment at L4 would be nearly identical to Earth's, since L4 sits at the same heliocentric distance. A spacecraft there would receive approximately 1,361 watts per square meter of solar flux, identical to Earth orbit, without the day-night cycle or atmospheric interference. The power budget for a solar-powered observatory at Sun-Earth L4 is achievable with conventional designs, without the exotic thermal engineering required for L2. From an observational standpoint, Sun-Earth L4 offers something neither L1 nor L2 can provide. A telescope at L4 could observe the Sun from a perspective displaced 60 degrees from Earth's line of sight. Combined with Earth-based solar observations, this would enable stereoscopic reconstruction of coronal structures in 3 dimensions, something impossible from a single vantage point. Active regions rotating away from Earth's view would remain visible from L4 for days longer, extending continuous monitoring of specific solar features across the full 27-day solar rotation period. No such mission has been formally approved, but the gravitational address is already there, silent and waiting, 150 million kilometers behind the Earth in its orbit, maintaining its equilibrium as it has since the solar system settled into its current configuration. The mathematical address that Lagrange computed in 1772 is increasingly a real address, a location in space to which hardware can be directed, at which hardware can be maintained, and from which hardware can operate indefinitely. The night is late. The pace of thought slows naturally with the pace of the universe, which is patient, which is unhurried, which has been arranging its geometry for 4.5 billion years and will continue arranging it long after any single mission or instrument or civilization has concluded. The 5 points exist around every planet. They existed before the planets formed, as potential features of whatever orbital configurations would eventually arise from the collapsing protoplanetary disk. They came into existence as stable or unstable equilibria as the planets settled into their current orbits. They have been filling slowly with material ever since: asteroids, dust, spacecraft, and perhaps, eventually, the first human structures in deep space. The mathematics that describes them is 250 years old. The physical reality they describe is 4.5 billion years old. The operational use humanity is making of them is less than 50 years old. The gap between the mathematics and the application is closing. And in the cold, dark space between the planets, in the 5 places where the forces of gravity resolve into silence, the geometry persists, as it has always persisted, waiting for whatever small thing is placed there next. The relationship between Lagrange points and the broader question of where humanity goes next in space is not merely speculative. It is now a design constraint in actual mission planning documents. The ESA Moonlight Initiative, a proposed commercial lunar communication and navigation service, identifies the Earth-Moon L2 halo orbit region as a primary relay node location. The Lunar Gateway's near rectilinear halo orbit is already a formally adopted architecture in the Artemis program. Multiple academic groups have published trajectory analyses for missions to Sun-Earth L4 and L5 as locations for space-based solar power collection, where the continuous solar illumination and stable orbital positions could in principle support large photovoltaic arrays, beaming power to Earth via microwave transmission. These proposals remain conceptual, but the progression from Lagrange's abstract mathematical solution to IC3's operational demonstration to Webb's scientific transformation to Artemis's cislunar infrastructure planning represents a clear and continuing trajectory in the operational use of Lagrange point geometry. The trajectory does not require exotic physics. It requires only the continued application of mathematics that has been understood for 2.5 centuries, combined with the incremental improvement of engineering capabilities that make what was impossible in 1978 routine in 2026, and what is ambitious in 2026 potentially routine in 2076. The 5 points are stable features of the solar system's gravitational landscape. They will be here for as long as the Sun and the planets maintain their current orbital relationships, for billions of years on the most conservative estimates. The window of opportunity they provide is by any human timescale permanent. What changes is not the points. What changes is what humanity is capable of placing there. IC3 was a 479-kilogram spacecraft carrying a handful of plasma and particle detectors. Webb is a 200-kilogram observatory with a 6.5-meter gold mirror. The Lunar Gateway will be a multi-module crewed outpost with a total mass of tens of thousands of kilograms. Each represents an increase in capability and ambition at the Lagrange point address that Lagrange computed and Farquhar proved accessible. The next entries in this progression are not yet built, but the locations they will occupy are already known. They are the 5 points of balance in a gravitational system that has been running for 4.5 billion years, silently organizing the motion of everything within its reach, offering 5 still addresses in the architecture of the solar system. 5 places where the mathematics resolves. 5 places where the universe briefly holds still. There is a number worth pausing on. In any two-body gravitational system, a star and a planet and a moon, a binary star system, 5 Lagrange points exist. The solar system contains 8 planets. It contains more than 200 known moons. It contains numerous binary asteroid systems, binary Kuiper belt objects, and the Sun itself as the primary mass in relation to each planetary body. A conservative count of distinct Lagrange point systems in the solar system, considering only the Sun-planet pairs and the major planet-moon pairs, exceeds 100. Each of these systems contains 5 equilibrium points. The total number of Lagrange points in the solar system across all the two-body systems that can be meaningfully defined within it is in the hundreds. Most of them contain nothing that humanity has placed there. Most of them have never been visited. Most of them have never been observed closely. Most of them are occupied by whatever the gravitational dynamics of the early solar system happened to deposit there, dust, asteroids, or simply empty space, and have remained in that state, unchanged, since before the first complex organisms appeared on Earth. The Lagrange points of Saturn's moon Titan in its relationship with Saturn are mathematically identical in structure to the Sun-Earth Lagrange points. The Lagrange points of Pluto and its moon Charon, a system in which the two bodies are so comparable in mass that they both orbit a common center of mass located above Pluto's surface, are more complex because the mass ratio approaches unity and the standard stability analysis requires modification. But the 5 equilibrium points still exist, with modified stability characteristics. The universe does not make exceptions to its mathematics. Wherever two masses orbit each other, the 5 points exist. The Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, each generate Lagrange point systems in their orbital relationship with Jupiter. The Jupiter-Europa L1 and L2 points sit close to Europa's surface, approximately 900 kilometers above the surface for L1 and L2 combined, because Europa is small and its gravitational influence is weak compared to Jupiter's. A spacecraft passing through the Jupiter-Europa L2 region could in principle be captured into a low-energy orbit around Europa from a Jupiter-centered orbit with less propellant than a conventional orbit insertion. This technique, using the manifold structure of a moon's Lagrange, points to approach the moon's sphere of influence with minimal delta V, has been studied extensively in the context of future Europa missions. The Europa Clipper spacecraft, launched in October 2024 and currently en route to Jupiter, will perform a series of Europa flybys during its mission. Its trajectory design incorporates gravitational assists from the Galilean moons to reduce the propellant required for each orbit adjustment around Jupiter. Europa Clipper will not park in a Europa orbit during its primary mission. The radiation environment near Europa is too severe for long-duration orbital operations. Instead, it will make dozens of close flybys, each one using the manifold adjacent geometry of the Jupiter-Europa system to approach and retreat efficiently. The science returned from these flybys will characterize Europa's ocean, ice shell, and surface chemistry in more detail than any previous mission. The detection of a liquid water ocean beneath Europa's ice shell, one of the most significant planetary science discoveries of the late 20th century, places Europa among the most scientifically compelling targets in the solar system. If liquid water exists beneath the ice, and if the ocean has contact with the rocky seafloor, then the conditions for hydrothermal chemistry, similar to that which supports deep-sea ecosystems on Earth, may exist there. The Lagrange point geometry of the Jupiter-Europa system is a practical tool for the engineers designing the mission trajectory, but the science question it enables, whether Europa's ocean hosts chemical conditions compatible with life, is among the deepest questions in planetary science. The 5 points of gravitational equilibrium, computed by a mathematician in the 18th century, are being used to search for life in the 21st. The scale of this progression, from abstract mathematics to the search for life in another world's ocean, is one of the genuinely extraordinary features of the history of science. Lagrange was not thinking about life on Europa. He was not thinking about spacecraft. He was thinking about the mathematics of 3 interacting gravitational fields, and he found a property of that mathematics that turned out to have applications that extend across every branch of planetary science and space exploration. This is a recurring pattern in the history of physics. James Clerk Maxwell derived the equations of electromagnetism in the 1860s, unifying electricity, magnetism, and optics into a single theoretical framework, radio communication and wireless transmission were not part of his inquiry, but the properties of electromagnetic waves that his equations predicted were the foundation of every technology that transmits information through the air or vacuum. Albert Einstein developed general relativity in 1915, describing gravity as the curvature of space-time caused by mass and energy. GPS satellites were not yet imaginable, but general relativistic corrections to the ticking rate of clocks in different gravitational fields and at different velocities are necessary for GPS systems to maintain the precision required for navigation. Without relativistic corrections applied continuously to the satellite clock signals, GPS positions would drift by approximately 10 kilometers per day. Lagrange found 5 equilibrium points in a restricted version of the three-body problem. He was not thinking about solar wind monitoring or infrared astronomy or Trojan asteroid populations or cislunar logistics, but the properties of those 5 points, their locations, their stability characteristics, their orbital families, their manifold structures, have turned out to be essential infrastructure for the most important scientific missions and space exploration programs of the modern era. The pattern is consistent. Pure mathematics, pursued for its own logical interest, eventually finds physical application in ways that could not have been anticipated at the time of discovery. The application may take decades or centuries, but the mathematics was always there, waiting to be used. The universe writes its operating instructions in mathematics. The instructions were written before anyone read them. The pace of the night slows here. The scientific content has been large. The distances covered in this story, from the 1.5 million kilometer halo orbits of L1 and L2 to the billions of kilometers of the outer solar system to the theoretical reaches of the Oort cloud, span the full scale of the solar system's architecture. The physics covered, from the saddle point instability of the collinear Lagrange points to the Coriolis-stabilized equilibrium of L4 and L5, from halo orbit mechanics to manifold tube networks, from cryogenic infrared astronomy to primordial asteroid chemistry, represents a substantial fraction of the scientific content of modern solar system exploration. All of it connected by 5 mathematical points. 5 locations that exist because 2 massive bodies orbit each other, and the combined gravitational and centrifugal forces in the rotating reference frame of that orbital system have 5 specific locations where the net force on a small object is 0. 5 locations that are invisible, massless, and permanent. The permanence deserves attention. The Lagrange points of the Sun-Earth system will exist as long as the Sun and Earth orbit each other. The Sun has approximately 5 billion years of main sequence life remaining before it expands into a red giant and eventually sheds its outer layers, leaving a white dwarf remnant. During the red giant phase, the Sun's mass loss will cause the planetary orbits to expand, and the Lagrange points will shift their positions accordingly. Eventually, if Earth survives the Sun's expansion, a matter of some uncertainty in current models, the Earth-Sun orbital relationship will end, and the Earth's Lagrange points will cease to exist. But that is 5 billion years away. On any timescale relevant to human civilization, to the history of life on Earth, to the existence of the solar system as a recognizable configuration of planets, the 5 Lagrange points of the Sun-Earth system are permanent features of the gravitational landscape. They were there when the first photosynthetic organisms evolved in Earth's oceans, approximately 3 billion years ago. The Cambrian explosion populated Earth's seas with complex animal life approximately 540 million years ago, and the 5 points were already there. They were there when the asteroid impact 66 million years ago ended the Cretaceous period and cleared the ecological space for the diversification of mammals. When the first members of the genus Homo appeared in Africa approximately 2.5 million years ago, the 5 points were already there. They were there when Lagrange was born in Turin in 1736. They were there when IC3 launched in 1978. They are there now, in the dark above, indifferent to the passage of time, holding their geometry with the precision of mathematics itself. The instruments at L2 are measuring photons from galaxies that formed when the universe was 300 million years old, less than 3% of its current age. The asteroids at Jupiter's L4 and L5 have been orbiting in their gravitational basins since before the Earth had an ocean. The solar wind detectors at L1 are measuring the properties of a stellar wind that has been blowing continuously for 4.5 billion years. All of this is happening now, simultaneously, in the solar system that exists above the atmosphere of this planet. The night is quiet. The orbital mechanics continue without interruption. The mathematics does not require supervision. Somewhere, 1.5 million kilometers in the direction of the Sun, a cluster of aging spacecraft performs its periodic station-keeping burns, a few meters per second of velocity change, a few grams of propellant, maintaining the geometry. Somewhere, 1.5 million kilometers in the opposite direction, a gold mirror cooled to 6 Kelvin is open to the dark sky, collecting ancient photons, converting them to electrons, packaging them as data, transmitting them to Earth. Somewhere, 5.2 astronomical units from the Sun, 60 degrees ahead of Jupiter in its orbit, ancient carbonaceous objects drift in their slow librations. 100 kilometers wide, dark as charcoal, chemically complex, 4.5 billion years old, completing their orbits while a spacecraft named for a hominid fossil travels toward them across the emptiness. The solar system does not announce itself, it simply continues. The orbits continue. The measurements continue. The mathematics holds. If this kind of science story is what brings you to sleep, this channel exists to keep delivering it. Quiet Science at Bedtime produces long-form science narration, real science, real measurements, real missions, designed to carry you into sleep on a current of genuine knowledge about the universe. A subscription and a like help this channel reach more people who might need exactly this. Notifications will bring the next episode to you. The universe is larger than any single episode can contain. The next story is already waiting. For now, the night is at its end. The 5 points remain. The mathematics holds, as it has always held, as it will continue to hold across the remaining 5 billion years of this solar system's existence. Silent, invisible, permanent. 5 places where gravity resolves into stillness. 5 addresses in the architecture of space that Lagrange found with a pen, that engineers reached with a rocket, and that telescopes and particle detectors and ancient asteroids occupy tonight, in the dark, above this turning planet. Everything you heard tonight is real. The Lagrange points are out there right now. The discovery of Lagrange points is, in one sense, a story about the power of restricted problems. The general three-body problem, three arbitrary masses interacting gravitationally, has no closed-form solution. Poincaré proved in 1890 that the general problem cannot be solved analytically in the sense that planetary orbits can be solved. The phase space of the general three-body problem is non-integrable. Trajectories are chaotic in the technical sense, exponentially sensitive to initial conditions, unpredictable over long timescales, resistant to analytical description. Lagrange did not solve the general problem. He found a restricted version that was tractable by assuming that one of the three bodies had negligible mass, that it was a passenger, not an actor, in the gravitational drama. He reduced the problem to one that had exact solutions. 5 of them. This strategy, finding a restricted version of an intractable problem that still yields useful results, is one of the most productive approaches in theoretical physics. It does not answer the question that was originally posed. It answers a nearby question that turns out to be the right question for practical purposes. The 5 Lagrange points are the answer to a restricted question, but they are the answer that matters for spacecraft. The spacecraft is always, to excellent approximation, a passenger in the gravitational field of the Sun and Earth. Its mass is negligible. Lagrange's restricted solution is the correct framework for its dynamics. The match between the mathematical restriction, negligible third-body mass, and the physical situation, spacecraft mass negligible compared to Sun and Earth, is not coincidental. It is why the restricted three-body problem is the right model for spacecraft trajectory design near Lagrange points. The physics selects the appropriate mathematical framework. This is a feature of the relationship between mathematics and physics that appears repeatedly in the history of science. The mathematical structure that turns out to be useful is often the one that was developed to answer an abstract theoretical question without any practical application in mind. The selection happens not because the mathematics was designed for the application, but because the mathematics correctly captures the structure of the physical situation. Lagrange's restricted three-body problem correctly captures the structure of spacecraft dynamics in the Sun-Earth gravitational field. Maxwell's equations correctly capture the structure of electromagnetic fields. General relativity correctly captures the structure of space-time curvature. In each case, the mathematics came first, and the application followed decades or centuries later. The universe was already running the equations before anyone wrote them down. The equations themselves have a kind of beauty that is independent of their applications. The effective potential of the rotating Sun-Earth system, the gravitational potential modified by the centrifugal term in the rotating reference frame, forms a landscape with a specific topology: 2 deep wells centered on the Sun and the Earth, a shallow well at L3 on the far side of the Sun, a ridge running between L1 and L2, with L1 and L2 sitting at the saddle points of this ridge, and 2 broader, shallower potential minima at L4 and L5, where the combined effect of the gravitational wells and the centrifugal term creates a local minimum rather than a saddle. This topological structure, the specific arrangement of wells, ridges, and saddle points, is determined entirely by the mass ratio between the Sun and Earth and the rotational dynamics of the system. It is a fixed geometric property of the gravitational field. Every physical consequence that has been discussed, the stability of L4 and L5, the instability of L1 and L2, the existence of halo orbits, The manifold tube network follows from this topology. The topology was there before the Earth formed. It came into existence when the Sun and its protoplanetary disk established the mass ratios that define it. It has been a feature of the solar system since before the Earth solidified from its molten early state. The topology is there tonight, above the atmosphere, in the gravitational field of the Sun and Earth. It is not observable. It is not luminous. It has no physical substance, but it is real as the field lines of a magnet, as real as the curvature of space-time around a massive object, as real as any other structure that exists in the mathematical description of physical reality, rather than as matter or energy directly. The 5 Lagrange points are features of this topology. They are the points where the gradient of the effective potential is 0, where the slope of the gravitational landscape in the rotating reference frame is flat. Objects placed there experience no net force. L4 and L5 are bowls in this landscape, shallow, curved depressions where the potential increases in every direction away from the center. Objects displaced from these bowls experience a restoring tendency. L1, L2, and L3 are mountain passes, saddle points where the potential increases in some directions and decreases in others. Objects displaced from these passes in certain directions experience an accelerating force away from equilibrium. The geometry is precise. The mathematics is exact. The topology was computed by Lagrange and has been confirmed by every spacecraft that has been sent to a Lagrange point and successfully maintained its orbit. The confirmation extends across decades, missions, and spacecraft generations. ICE-3 confirmed it in 1978, SOHO confirmed it in 1996, WMAP confirmed it in 2001, Herschel and Planck confirmed it in 2009, Gaia confirmed it in 2013, Webb confirmed it in 2022. Each confirmation added another data point to the validation of a mathematical result that was never in serious doubt, but that now has the weight of operational reality behind it. Lagrange's solution works. The halo orbits are real. The manifold tubes are real. The Trojan swarms are real. The entire architecture of gravitational geometry that was implicit in the restricted three-body problem has been confirmed, piece by piece, by the accumulated history of space exploration. The confirmation is not complete. Neptune's Trojan swarm has not been fully characterized. The Earth-Moon Lagrange points have not been fully exploited. The manifold tube network of the outer solar system has barely been explored. The Lagrange points of the Galilean moon systems around Jupiter have never hosted a dedicated spacecraft. The exploration is ongoing. The mathematics is far ahead of the hardware, as it has always been since 1772. The night is deepening now. The sentences grow shorter. The distances remain. Above the atmosphere, the instruments continue their work in silence. Webb's mirror is open. The solar wind is measured. The Trojan's orbit. The 5 points hold their geometry with the indifference of mathematics, not caring whether anything rests there, not requiring an observer, not changing with the passage of time. They hold. They have always held. They are holding now, in the dark, 1.5 million kilometers in 2 directions from this planet, and 5 astronomical units ahead and behind Jupiter, and 30 astronomical units ahead and behind Neptune, and at every other scale and distance where two masses orbit each other in this ancient solar system. The universe is full of these still places. 5 for every pair of orbiting masses. Hundreds in this solar system alone. And in the stillness of this particular night, in the quiet between one breath and the next, the mathematics holds its balance above the turning Earth, as it has held since before the first cell divided in the first warm ocean on this planet. Still, balanced, real. If tonight brought you something, a fact, a distance, a sense of how large and how old and how structured the solar system is, please consider subscribing to Quiet Science at Bedtime. A like on this video, a notification turned on, a subscription. These are the things that allow this channel to continue bringing science into the quiet hours. Share it with someone who needs a long, slow, science-filled night. The next episode is already waiting in the dark. For now, good night. Sleep well. The 5 points are out there in the gravitational field above you, holding their geometry in the silence of the solar system. Everything you heard tonight is real. The Lagrange points are out there right now,